Please subscribe to support the channel. The question of how matter came from nothing is perhaps the deepest riddle humanity has ever faced. Every culture, every civilization, and every curious mind has at some point stared into the mystery of existence and wondered, why is there something instead of nothing? But the form that grips modern science, the one that challenges physicists and cosmologists today, asks specifically, how can matter itself, the building blocks of stars, planets, and people, arise from nothing at all? Think about what that question really means. Matter is not just the stuff we can touch, like rocks, trees, or oceans. It's the atoms that make them up, the subatomic particles inside those atoms, and the fundamental fields that govern how those particles behave. Matter is the very fabric of the physical universe. If you were to remove matter, what would remain? Would it be empty space? Pure nothingness? Or something stranger that we don't yet have words for? This is what makes the question so electrifying. On the surface, it feels impossible. We've been taught that nothing comes from nothing. Everything we see in daily life has a source. A house is built from bricks, which were made from clay, which came from minerals in the earth. A tree grows from a seed, nourished by soil, water, and sunlight. Even when something seems to vanish, like when wood burns into smoke, the matter isn't destroyed, it changes form, conserved according to the laws of physics. So if matter can't come from nothing in our everyday world, how could the entire universe, filled with galaxies stretching across billions of light-years, have emerged from nothing at all? This paradox is what makes the question both unsettling and irresistible. It pushes us to the very edge of human understanding. If we say that matter has always existed, then we're suggesting that something infinite and eternal has been with us all along, with no beginning. If we say matter was created, then we must ask, created from what? And if we dare to say matter came from nothing, then we must carefully examine what nothing really means, because it may not be as empty as we think. This question doesn't just belong to science. It touches philosophy, theology, metaphysics, and even the human imagination. Yet today, physics and cosmology take it seriously, treating it not as a poetic riddle but as a problem that can be studied, modeled, and debated with equations, theories, and observations. The hook is simple but profound. When we ask how matter came from nothing, we are asking the ultimate origin story. Not just how planets formed, or how life began, but how existence itself first took root. It's a question so vast that even to attempt an answer is to stand in awe of the cosmos. And yet, it is also a question that science is bold enough to wrestle with. The mystery of how matter could emerge from nothing is not confined to abstract thought or speculative philosophy. It is a puzzle that modern physics and cosmology have been forced to confront head-on. What makes this so fascinating is that, for much of human history, the idea of something from nothing was treated as a kind of intellectual curiosity, the type of riddle one might ponder in long philosophical debates without expecting any kind of concrete resolution. Ancient philosophers like Parmenides argued that nothing comes from nothing, a principle that seemed self-evident, while others speculated about eternal cycles of existence, or worlds arising out of chaos. For centuries, the question lingered in the realm of metaphysical speculation, where answers depended more on logical reasoning or spiritual conviction than on empirical evidence. But the landscape changed dramatically in the 20th century. Astronomy and physics began to reveal that the universe itself had a history, a beginning, an unfolding sequence of events, a timeline that stretched backward into an origin point. Observations made by Edwin Hubble in the 1920s, showing that galaxies are moving away from one another, suggested that the universe was expanding. That discovery, shocking at the time, implied that if you rewound cosmic history, everything we see today must once have been compressed into an unimaginably small, dense, and hot state. This gave rise to the modern Big Bang theory. And with it came the startling realization that the universe had not always existed in its current form. It had a beginning. This is where physics was forced to enter territory once reserved for philosophy. Because if the universe had a beginning, then what happened before that? Was there a time before time? Was there an existence before existence? Or did everything, the space, the time, the matter, the laws of physics themselves, emerge together, all at once, out of some primordial nothing? Suddenly, the ancient question of how something can arise from nothing was no longer just a matter of speculation. It became a scientific issue, one pressed upon us by observation and evidence. Cosmologists began to wrestle with this in earnest. The Big Bang was not simply an explosion of matter into pre-existing empty space. It was the birth of space itself, the unfolding of time, and the emergence of the conditions that allowed matter to exist. The laws of physics, gravity, quantum mechanics, relativity, all became central players in this puzzle. But if the laws of physics govern how matter behaves, where did those laws come from? Were they present before the universe existed, waiting in some abstract form? Or did they, too, emerge with the universe itself? This is where science finds itself brushing against the boundary of philosophy once again. Yet science is not content with leaving the mystery at the boundary. Physicists and cosmologists try to push deeper, armed with theories and mathematics. Quantum field theory shows us that what we might call empty space is not truly empty but filled with activity. Particle physics experiments confirm that the vacuum itself behaves in ways that suggest energy and fluctuation. General relativity, Einstein's great insight, ties the fabric of spacetime itself to the matter and energy within it. Together, these theories create a picture in which the birth of matter from nothing is not simply a miracle or a metaphysical claim, but something that might be explained, at least in part, by the known rules of the universe. This is why the question is so compelling to modern scientists. On one hand, it touches the ultimate boundary of what we can know, the very first moment, the birth of the universe, the instant when existence itself came to be. On the other hand, it is also a question that physics is uniquely positioned to explore. The study of high-energy particles in accelerators, the analysis of cosmic microwave background radiation left over from the early universe, and the use of mathematical models of quantum mechanics all give scientists tools to approach what was once thought unapproachable. And so the mystery is framed. It is no longer enough to say nothing comes from nothing and leave it there. The universe forces us to confront the possibility that our assumptions about nothingness may be wrong. Perhaps nothing in the philosophical sense, complete absence of space, time, matter, energy, and laws, is not the same as nothing in the scientific sense. Perhaps what physicists call nothing is a fertile quantum vacuum, brimming with fluctuations and possibilities. Or perhaps nothing is an unstable state that naturally gives rise to something, because the balance of energy and the rules of quantum mechanics demand it. The key point is that this is not idle speculation. Physicists and cosmologists treat this as a serious question, one that can be studied, tested, and refined with evidence. When Stephen Hawking wrote about the possibility that the universe can be self-contained, requiring no external cause, he was not writing poetry. He was attempting to describe a model consistent with the laws of physics. When other scientists discuss quantum fluctuations birthing universes, they are not indulging in science fiction but in hypotheses rooted in mathematics. These efforts do not yet give us a final answer, but they demonstrate that the mystery is not being ignored. It is being wrestled with directly, in the same spirit with which science has tackled other seemingly impossible questions. And this is what makes the question so thrilling. We are not talking about some obscure corner of theoretical thought. We are talking about the fundamental question of why there is a universe at all, why there is matter to form stars and galaxies, why there is a stage upon which life can emerge, and why you and I are here to contemplate it. It is a question at the boundary of physics and philosophy, but one that physics has claimed as its own challenge. The sheer audacity of that is remarkable. It shows the power of human curiosity, that we dare to ask not only how stars shine or how galaxies evolve, but how existence itself arose from what we call nothing. The mystery, then, is framed in a way that both humbles and inspires. It reminds us that science is not only about solving practical problems or inventing new technologies, it is also about chasing the deepest truths of reality. The effort to explain how matter could arise from nothing is one of the boldest quests ever undertaken, one that pushes the limits of our theories, challenges our assumptions, and forces us to stand in awe of the cosmos. It is not merely philosophy, and it is not merely physics. It is the union of both, working together in humanity's never-ending search to understand how it all began. When we take on the question of how matter could arise from nothing, we quickly run into a critical issue. What do we actually mean when we use the word nothing? At first glance, the word seems obvious. Nothing should mean exactly that, the absence of everything. But when we begin to look deeper, we discover that nothing is not so simple. In fact, it has multiple meanings, and the way we define it radically changes how we approach the problem of matter's origin. If we aren't precise about what nothing means, then we risk misunderstanding the entire question. In ordinary language, people often use nothing in a casual sense. If someone asks what's in a box and you reply nothing, you usually mean that the box is empty of noticeable contents. But even an empty box isn't truly nothing. It contains air molecules, traces of radiation, even the space itself that the box occupies. This everyday sense of nothingness is more about the absence of obvious things, not the absence of everything. The philosophical and scientific discussions demand a far stricter definition. Philosophers, when they speak of nothing, often mean absolute nothingness. This is not just the absence of matter or objects, but the absence of space, time, laws, energy, everything. Imagine not a blank void, not a dark emptiness, not even a vacuum, but the complete lack of existence itself. No dimensions, no background, no framework upon which anything could exist. This is nothing in its purest sense, a kind of conceptual zero. Many philosophers argue that this absolute nothingness is the most fundamental version of the word, and therefore, when we ask how matter could arise from nothing, this is the definition we should keep in mind. But this definition poses a serious problem. If truly nothing exists, then how could anything ever arise? If there are no laws, no possibilities, no conditions, then how could a universe suddenly appear? This is the paradox that makes the philosophical version of nothing so challenging. Scientists, however, often use the term nothing in a different way. In physics, what is sometimes called nothing is really what's known as the vacuum state. A vacuum might appear empty because it lacks particles and matter, but in reality it is far from nothing. According to quantum field theory, the vacuum is a seething field of activity. Even in what seems like empty space, quantum fluctuations constantly occur. Particles and antiparticles flicker in and out of existence, borrowing energy from the void and then annihilating back into nothingness in unimaginably short timescales. This is what is known as the quantum vacuum, and it is very different from the philosophical idea of nothingness. The quantum vacuum has properties, energy, and structure. It is governed by physical laws. In this sense, nothing in science often means the lowest possible energy state of space, which is very much a kind of something. There's also a middle ground definition that often confuses people, the idea of empty space. Imagine clearing out all matter, all radiation, and all particles from a region of the universe. What you would be left with is pure space, no air, no light, no dust, just emptiness. But even this isn't true nothingness. Space itself has geometry. It can expand, curve, and bend according to the rules of general relativity. Empty space is still something, because it provides a stage upon which matter and energy can exist. The very fabric of space-time is not nothing but a kind of physical entity that can carry energy and be influenced by gravity. So, when we speak of nothing, we must ask, are we talking about philosophical nothing, where no existence of any kind is possible? Are we talking about empty space, where matter has been stripped away but the fabric of space-time remains? Or are we talking about the quantum vacuum, where fluctuations and potentiality hum beneath the surface of apparent emptiness? These distinctions are not just academic, they fundamentally shape the way we think about the origins of matter. For example, if we take the philosophical definition, then explaining the origin of matter becomes a near impossible puzzle. If truly nothing existed, with no framework or laws, then the sudden appearance of matter seems inexplicable. But if we use the physicist's definition, then the situation looks very different. In a quantum vacuum, particles can and do appear spontaneously. The vacuum is not inert but alive with possibility, and under the right conditions, those fluctuations could grow into the seeds of a universe. This is why clarifying the meaning of nothing is so important. Without this step, we risk talking past one another. A philosopher might say that science cannot explain how something came from nothing, because the vacuum of physics is not true nothing. Meanwhile, a physicist might argue that the nothing they study is sufficient to explain how particles could emerge. Both are correct within their own frameworks, but they are talking about different concepts. Ultimately, when we ask how matter came from nothing, we are often weaving between these definitions. The everyday sense of nothing, an empty box or an empty room, is not relevant at the cosmic scale. The philosophical sense of absolute nothingness raises paradoxes that may be beyond scientific reach. And the scientific sense of nothing, the quantum vacuum, gives us models and mechanisms that at least point to ways matter could emerge spontaneously. Each definition reveals a different layer of the mystery, and all must be kept in mind if we are to wrestle honestly with the question. Clarifying this distinction doesn't solve the problem, but it makes the puzzle clearer. Perhaps the ultimate truth is that nothing in the strictest sense has never really existed, and what we call nothing always carries the seeds of something. Or perhaps there was indeed an absolute nothing, and the birth of matter required a leap beyond our current imagination. Either way, the precision of our definitions is crucial, because before we can explain how matter came from nothing, we must first understand what nothing really is. When we confront the idea of philosophical nothingness, we enter some of the most difficult and mind-stretching territory that human thought has ever attempted to navigate. Philosophical nothingness is not simply the absence of objects, particles, or energy. It is not a vacuum, not empty space, not even a void in the scientific sense. It is the total absence of everything. No space to contain anything. No time to measure moments. No laws to govern interactions. No framework, no background, no canvas upon which something could appear. It is an absolute negation of existence, a state, if we can even call it a state, that is beyond all categories we use to describe reality. This version of nothingness is notoriously difficult to even imagine, because our minds are shaped by a world of something. When we think of nothing, we often picture a dark, empty void. But even that image is misleading. Darkness is still a property. Emptiness is still space. A void implies a location where something could potentially be. Philosophical nothingness, however, allows no such background. It is the absence of any place, any condition, any possibility. It is pure non-being. Philosophers have long debated whether such nothingness is even coherent. Can we meaningfully speak of nothing in this absolute sense? Some argue that the very act of conceiving it introduces a contradiction, because the moment we think about nothing, we are already treating it as if it were a kind of something, as if it had qualities, or could be distinguished from other things. Others insist that absolute nothingness is necessary as a concept, because without it, we cannot fully grasp the contrast with being. To talk about something, we must acknowledge the possibility of its opposite. The ancient Greek philosopher Parmenides was one of the first to wrestle with this issue. He argued that nothing cannot exist, because if it did exist, it would in some sense be something. For him, being was fundamental and eternal, and non-being was impossible. Fast forward to modern philosophy, and the problem remains just as thorny. Existentialist thinkers like Martin Heidegger framed the central question of metaphysics as, why is there something rather than nothing? This is not just a scientific question about processes, but a fundamental puzzle about existence itself. Heidegger suggested that nothingness is not simply an absence, but a concept that confronts us directly in our awareness of being. For others, like Jean-Paul Sartre, nothingness was intimately tied to consciousness itself, a kind of gap or freedom within existence that allows humans to transcend the given. But when it comes to the origins of the universe, philosophical nothingness poses perhaps the most daunting challenge. If there were truly no space, no time, no laws, and no conditions, how could a universe ever arise? The problem here is that emergence seems to require a context. To say something appeared implies a before and after, a location of appearance, and a rule governing how such an event could happen. Absolute nothingness gives us none of these. By definition, it contains no potential, no possibility. It is absolute absence. And yet, here we are, living in a universe filled with galaxies, stars, and matter. This paradox forces us into a corner. Either we must accept that absolute nothingness never truly existed, and that there has always been some kind of something, whether it be matter, energy, laws, or potentiality, or we must face the near incomprehensible idea that existence somehow leapt out of absolute non-existence. The second option seems impossible according to our intuition, and yet it is precisely this puzzle that makes the question so captivating. One way philosophers sometimes attempt to soften the paradox is to argue that nothingness is unstable. If nothingness truly lacks everything, then perhaps it also lacks stability. Some suggest that it is in the nature of nothing to give rise to something, as strange as that sounds. In this view, Being inevitably emerges because absolute non-being is an impossible condition to sustain. But critics point out that this explanation is slippery, because if nothing has no properties, then how can it be unstable? Instability itself would be a property, a law, a feature, exactly the kind of something that nothingness supposedly excludes. What becomes clear is that philosophical nothingness pushes us beyond the limits of language and reasoning. Every attempt to describe it seems to smuggle in the qualities of existence. Every effort to explain how something could arise from it risks turning nothing into a hidden kind of something. It may be that absolute nothingness is a concept useful for contrast but meaningless as an actual state of affairs. It may be that the universe never came from pure nothingness at all, but from a deeper reality we don't yet understand. Still, the very act of considering philosophical nothingness has value. It forces us to grapple with the boundaries of thought. It highlights the astonishing fact that we live in a universe where being exists. It presses upon us the mystery that has haunted thinkers for centuries. If absolute nothingness is the default, why does being triumph? Why is there existence, when non-existence seems so much simpler? This is the puzzle at the heart of the philosophical idea of nothingness. It may not give us clear answers, but it deepens our sense of the problem. And it reminds us that when we talk about matter arising from nothing, we must carefully distinguish between the absolute void of philosophy and the more structured vacuums of science. Because if we mean absolute nothing, no space, no time, no laws, then the leap to a universe filled with galaxies is nothing short of miraculous. When we move from the realm of philosophy into the realm of physics, the meaning of nothing undergoes a dramatic transformation. The scientist's nothing is not an absolute void without potential or properties, but something far more complex and, in many ways, far more intriguing. In physics, when researchers talk about nothing, they often mean the vacuum, a state that looks empty to us, yet is brimming with activity beneath the surface. This scientific version of nothing turns out to be a dynamic foundation from which matter can indeed arise. To the naked eye, or even to a powerful telescope pointed into the depths of intergalactic space, a vacuum looks like emptiness. No stars, no planets, no gas clouds, just dark void. But appearances deceive. What quantum mechanics has taught us is that even the most seemingly barren region of space is not truly empty. It is filled with fields, invisible but fundamental, that permeate the cosmos. According to modern physics, particles are excitations in these fields. So even if no particles are present, the fields themselves remain. And those fields are restless. They are never perfectly still, never perfectly at zero. They quiver, jitter, and fluctuate constantly, thanks to the principles of quantum uncertainty. This means that the vacuum of space is not a silent, dead nothingness but a frothing sea of possibilities. At incredibly tiny scales, particles and antiparticles pop in and out of existence for fleeting moments before annihilating each other again. These virtual particles, as they are called, cannot be directly observed in the usual sense, but their effects are measurable. They alter the behavior of atoms, shift the energy levels of electrons, and even influence how the universe expands. So when physicists say that nothing can produce particles, they don't mean absolute nothing. They mean that the vacuum itself, through its restless fluctuations, has the capacity to give rise to transient forms of matter. The scientific version of nothing is therefore paradoxical. It is the lowest possible energy state, and yet it contains energy. It is a space without particles, and yet it generates particles. It is a baseline of reality, but one that never truly rests at zero. This is not merely a mathematical curiosity. Experiments confirm it. For example, the Casimir effect demonstrates that two uncharged metal plates placed extremely close together in a vacuum will experience an attractive force. Why? Because the vacuum between them is not truly empty. Quantum fluctuations of fields are restricted between the plates compared to outside, creating a measurable pressure difference. This is evidence that empty space is alive with unseen energy. Another striking piece of evidence comes from cosmology itself. The accelerating expansion of the universe, attributed to what we call dark energy, might be rooted in the properties of the vacuum. If the vacuum has energy, even when devoid of matter, then this energy exerts a repulsive gravitational effect, pushing galaxies apart at ever faster rates. Thus, the scientific concept of nothing may not just be an abstract idea, It could be the dominant force shaping the fate of the entire universe. This stands in stark contrast to philosophical nothingness. Philosophical nothingness has no laws, no structure, no potential. Scientific nothing, by contrast, has laws built in. It is governed by quantum mechanics and relativity. It has energy, even if that energy is invisible and subtle. It has structure, in the form of fields and fluctuations. It may not contain matter as we normally think of it, but it is fertile ground from which matter can emerge. In fact, many physicists argue that our universe itself could have arisen from a quantum fluctuation in this kind of vacuum state. If so, then what we call nothing might actually be the womb of everything. It's worth emphasizing that this is not sleight of hand or playing tricks with language. Scientists are not redefining nothing to mean something just to avoid the problem. Rather, they are working with the evidence that reality provides. When experiments show that empty space produces measurable forces, or when equations predict that vacuum energy contributes to cosmic expansion, then the conclusion is unavoidable. What we casually call nothing is not truly nothing. It is a physical entity with properties that we can study. And this raises fascinating philosophical questions of its own. If the scientific nothing is really a structured vacuum full of activity, then it is not absolute nothingness. That means the ultimate question, why is there something rather than nothing, remains unresolved. Because one could still ask, why does the quantum vacuum exist? Why do the laws of quantum mechanics operate at all? If the vacuum is the source of matter, then what is the source of the vacuum? The scientific version of nothing explains how particles can arise, but it does not necessarily explain why the stage for their appearance exists in the first place. Yet even with that caveat, the scientific idea of nothing has revolutionized our understanding of the cosmos. It shows us that the line between nothing and something is blurrier than we once imagined. It suggests that the fabric of reality is far richer than our intuition leads us to believe. And it opens the door to the possibility that matter did not require an external cause to appear, but could have emerged naturally from the restless energy of the vacuum itself. The contrast could not be clearer. Philosophical nothingness is an absolute void beyond conception. Scientific nothingness is a quantum vacuum, humming with invisible energy and capable of birthing particles. The first seems incapable of producing a universe. The second offers a plausible mechanism for how matter might arise spontaneously. And it is in this scientific version of nothing that cosmology finds a foothold, a way to move from mystery toward explanation, without claiming to have reached the final truth. One of the most astonishing discoveries of modern physics is the realization that empty space is not truly empty. What we once thought of as barren nothingness turns out to be a kind of boiling cauldron at the smallest scales, a restless ocean where particles and antiparticles continually bubble into existence and vanish almost instantly. This phenomenon is known as vacuum fluctuations, and it is a direct consequence of the strange rules of quantum mechanics. To understand vacuum fluctuations, we must first grasp the quantum view of reality. Unlike classical physics, which assumes that things can be perfectly still or perfectly empty, quantum mechanics insists that uncertainty rules at the most fundamental level. According to the Heisenberg uncertainty principle, there are limits to how precisely certain properties can be known simultaneously. For example, you cannot know both the exact position and the exact momentum of a particle at the same time. Similarly, when it comes to energy, the uncertainty principle allows fluctuations to occur in what we would otherwise expect to be a vacuum. Think of it this way: in classical physics, a vacuum should mean zero energy, zero particles, total stillness. But quantum mechanics doesn't permit such perfect stability. Instead, the vacuum always has a residual zero-point energy. This means that even when we strip away all particles and radiation, space itself retains an irreducible jitter. That jitter manifests as fluctuations in the quantum fields that permeate the universe. These fluctuations are not abstract. They are real enough to produce fleeting pairs of particles and antiparticles that spontaneously appear, borrow energy from the vacuum, and then annihilate back into non-existence within unimaginably tiny fractions of a second. At first glance, this might sound like science fiction, but experiments confirm it. For example, the famous Casimir effect provides strong evidence of vacuum fluctuations. When two metal plates are placed very close together in a vacuum, the fluctuating quantum fields outside and between them create an imbalance, leading to a tiny but measurable attractive force. This force cannot be explained without acknowledging the restless energy of the vacuum. In other words, the plates are being pushed together not by any external matter but by the seething activity of empty space itself. Vacuum fluctuations also play a role in atomic physics. They slightly shift the energy levels of electrons in hydrogen atoms, an effect known as the Lamb shift, which has been measured with exquisite precision. Once again, the explanation points back to the fluctuating fields of the vacuum. What appears to be empty is, in fact, influencing the structure of atoms themselves. But perhaps the most profound implication of vacuum fluctuations lies in cosmology. Some theories suggest that the entire universe might have sprung from a fluctuation in the vacuum. If the vacuum is never truly empty but always bubbling with possibilities, then perhaps under rare and extreme conditions, one of these fluctuations could have inflated into an entire cosmos. In this scenario, our universe would not be an exception to the rule, but the ultimate expression of the vacuum's restless creativity. What makes this idea so compelling is that it doesn't require anything external to cause the appearance of matter. The fluctuations are built into the fabric of quantum mechanics. They happen inevitably, without needing an outside agent. The universe itself, in this picture, is a grand-scale version of what happens all the time at the quantum level. Particles appearing out of apparent emptiness, sustained for only as long as the uncertainty principle allows. It is important to emphasize that these fluctuations are not just theoretical constructs, they have real consequences that shape our universe. Without them, the laws of physics as we know them would not match experimental evidence. They are not optional quirks of theory, but central features of reality. And they force us to radically rethink the idea of nothingness. If even the emptiest space is bubbling with activity, then nothing is not nothing at all, it is a fertile background filled with potential. This challenges our intuition in profound ways. We tend to imagine nothing as a calm void, a perfect blank. But the quantum vacuum is more like the surface of a boiling pot of water, constantly fizzing and shifting at scales too small for us to perceive directly. We are accustomed to thinking of something arising from nothing as an impossibility, but in quantum mechanics, this bubbling activity is not only possible, it is unavoidable. In fact, vacuum fluctuations are so fundamental that some scientists speculate they may even provide the seeds of structure in our universe. During the earliest moments after the Big Bang, rapid cosmic inflation could have stretched these tiny fluctuations to cosmic scales, seeding the distribution of galaxies and clusters that we observe today. If true, this means that the grand architecture of the cosmos, the galaxies scattered across billions of light-years, owes its existence to the restless bubbling of the quantum vacuum in the first instant of creation. So when we speak of vacuum fluctuations, we are speaking of more than a quirky detail of physics. We are speaking of the possibility that everything we see, the stars in the sky, the earth beneath our feet, and our very selves, may be the echoes of quantum jitters in what we once mistakenly called nothing. Far from being empty, the vacuum is alive, dynamic, and creative. It blurs the boundary between nothing and something, showing us that the transition from one to the other may not be a leap at all, but a continuous process that happens everywhere, all the time. When we talk about vacuum fluctuations, one of the most fascinating consequences is the appearance of what physicists call virtual particles. These strange entities are not like the everyday particles that make up the atoms in your body or the photons of light that stream from the sun. Instead, virtual particles are fleeting, ghost-like pairs of particle and antiparticle that erupt spontaneously out of the quantum vacuum, exist for a tiny fraction of a second, and then vanish as suddenly as they appeared. Though they are temporary and elusive, they are real enough to leave measurable marks on the universe, and they force us to reconsider what we mean by existence itself. To understand virtual particles, we need to recall that the quantum vacuum is not a calm void but a restless sea of fluctuations. These fluctuations momentarily provide enough energy to allow a particle and its mirror opposite, an antiparticle, to appear. For example, an electron might momentarily be paired with its antiparticle, the positron. Because of the rules of quantum mechanics, these pairs do not need to obey the same strict conservation laws that ordinary particles must. They can borrow energy from the vacuum as long as they repay it by annihilating one another quickly enough, disappearing back into the nothingness from which they came. This is why they are called virtual. They are not stable, observable particles in the normal sense, but ephemeral manifestations of the vacuum's jittering energy. They cannot be detected directly in isolation because they exist for such incredibly short durations. Timescales so brief that they are beyond human intuition, sometimes measured in intervals as small as 10 squared to the power of 1 seconds or less. Yet despite their fleeting lives, virtual particles exert real effects. One striking example is the phenomenon known as Hawking radiation. According to Stephen Hawking's theory, black holes are not perfectly black. Near the event horizon, virtual particle pairs constantly appear. Normally, these pairs annihilate each other instantly. But if one member of the pair falls into the black hole while the other escapes, the balance is broken. The escaping particle becomes real and radiates away into space, while the black hole loses a tiny bit of its mass to compensate. Over unimaginably long timescales, this process means that black holes can slowly evaporate. This radical prediction, born from the behavior of virtual particles, links quantum mechanics, relativity, and cosmology in a way that no one expected before Hawking's insight. Virtual particles also play a key role in more familiar physics. They mediate the fundamental forces of nature. For example, the electromagnetic force between two charged particles can be described as the exchange of virtual photons. These virtual photons are not real in the sense of detectable light, but they exist long enough to transmit the influence of one charge to another. Similarly, the strong nuclear force that binds quarks inside protons and neutrons can be modeled as an exchange of virtual gluons. In this sense, virtual particles are not peripheral oddities, they are central to how the universe holds itself together. Their influence even shows up in precise laboratory experiments. The Lamb shift, a tiny shift in the energy levels of electrons in hydrogen atoms, can only be explained by the presence of virtual particles interacting with the electron. Likewise, the anomalous magnetic moment of the electron, a slight deviation from what classical theory would predict, arises from the dance of virtual particles in the vacuum. These effects are measured with such accuracy that they provide some of the most stringent tests of quantum electrodynamics, the most successful theory in physics. But perhaps the most mind-bending aspect of virtual particles is how they challenge our understanding of what it means to exist. If a particle can appear and disappear without leaving a trace, does that count as real? If its presence can be inferred through measurable effects, is it less real than the particles we can directly observe? Physics forces us to admit that reality is not so black and white. Existence is not a binary of being or non-being. Virtual particles occupy a strange in-between, a twilight zone where potential and actuality blur. Some physicists even speculate that entire universes might be born in a similar way, as if the quantum vacuum itself produces not just particles but whole bubbles of space-time. In that case, what we call our universe may be the large-scale counterpart of the same phenomenon that allows a virtual particle to flicker briefly into being. The difference is only one of scale and persistence. To put it simply, virtual particles remind us that what we see as stable and permanent may ultimately be built on a restless foundation. They are the whispers of the vacuum, appearing just long enough to remind us that emptiness is never truly empty. Without them, the fundamental forces of the universe would not operate the way they do, atoms would not behave the way they do, and black holes would not evaporate. Their existence, paradoxical, fleeting, and invisible, teaches us that reality is deeper and stranger than our everyday intuition can grasp. Virtual particles, then, are not just mathematical tricks or convenient fictions. They are real in the sense that their presence is required to explain observations and experiments. They are the physical expression of the vacuum's restlessness. They show us how quantum mechanics allows matter to appear from what looks like nothing. And they remind us that the distinction between something and nothing may be far less clear-cut than we ever imagined. At the heart of quantum mechanics lies one of the most profound and counterintuitive ideas in all of science, the uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle tells us that there are fundamental limits to how precisely we can know certain pairs of physical properties at the same time. For example, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not just a limit of our measuring tools, it is a limit built into reality itself. Nature is inherently fuzzy at the smallest scales. This fuzziness is not a defect but a feature. It is the very reason that the microscopic world does not behave like the macroscopic world of everyday objects. And one of its most fascinating consequences is that it allows the temporary creation of energy and particles seemingly from nothing. Here's how it works. In classical physics, the conservation of energy is an absolute law. Energy cannot be created or destroyed, only transformed. But in quantum mechanics, conservation laws operate under the allowance of uncertainty. The uncertainty principle says that the energy of a system and the time over which it is measured form a complementary pair, much like position and momentum. The more precisely you know the energy, the less precisely you can know the duration over which that energy exists, and vice versa. This relationship opens a loophole. For very short spans of time, energy can borrow from nothingness, creating fluctuations that would be impossible under classical rules. In practical terms, this means that the vacuum of space can spawn particle-antiparticle pairs out of sheer uncertainty. These pairs are born, live briefly, and then annihilate back into the vacuum, returning the borrowed energy before anyone notices. The shorter the lifetime of the fluctuation, the more energy it can briefly access. This is why vacuum fluctuations are so fleeting. Quantum mechanics demands that the books be balanced, but it allows the balance to be temporarily broken if the debt is repaid quickly enough. This is the mechanism that makes virtual particles possible. They exist because the uncertainty principle allows tiny violations of energy conservation over extremely short timescales. Without Heisenberg's rule, the vacuum would be perfectly inert, an unchanging nothingness. With it, the vacuum becomes dynamic, alive with possibility. The universe is not a static ledger of energy but a system that tolerates short-term deviations, like a cosmic bank allowing overdrafts that must be repaid almost instantly. The implications are staggering. One is that the boundary between something and nothing is not as rigid as we once thought. If energy can emerge spontaneously, even temporarily, then nothing is not absolute emptiness but a stage where something is always threatening to appear. Another implication is that the laws of physics themselves may be written in a way that allows for self-generation. The universe doesn't need an external push to produce activity. Uncertainty ensures that activity is unavoidable. The uncertainty principle is not just a curiosity, it has been confirmed in countless experiments. It explains why electrons in atoms do not spiral into the nucleus. If electrons were perfectly localized at the nucleus, their momentum would become infinitely uncertain, giving them infinite kinetic energy. Instead, they occupy orbitals with a balance of uncertainty that stabilizes atoms. In other words, your very existence depends on the uncertainty principle. Without it, matter would collapse, chemistry would not exist, and life would be impossible. At the cosmic scale, this principle has even more dramatic implications. Some cosmologists suggest that the entire universe might be a giant fluctuation permitted by uncertainty. If the total energy of the universe balances out to zero, positive energy in the form of matter and radiation cancelled by negative energy in the form of gravity, then the universe could, in principle, emerge from nothing without violating any law. The uncertainty principle would provide the wiggle room for such a fluctuation to occur, and once it happened, inflationary expansion could magnify it into the vast cosmos we see today. It is hard to overstate how radical this is. A law that appears at first to be about the limits of measurement turns out to be a gateway to the possibility of existence itself. The uncertainty principle tells us that absolute nothingness, a perfectly still, perfectly empty void, is forbidden. There will always be jitter, fluctuation, unpredictability, and in those fluctuations lies the seed of everything: particles, forces, galaxies, and eventually, us. So the next time we wonder how matter could have come from nothing, we must remember Heisenberg's insight. Nothingness is not the lifeless emptiness we once imagined. It is unstable, restless, and pregnant with possibility. The uncertainty principle ensures that the universe cannot help but produce activity, even if only for an instant. And perhaps, just perhaps, it is this fundamental fuzziness that made it possible for our universe to take its first breath. When we look up at the night sky, it feels overwhelming to think of the sheer scale of energy that fills the universe. Every star is a nuclear furnace, every galaxy contains billions of stars, and the cosmos as a whole brims with unimaginable amounts of matter and radiation. At first glance, it seems absurd to even suggest that such a universe could have come from nothing. How could all this energy simply appear without some external source or cause? Yet modern physics proposes something deeply counterintuitive: that the total energy of the universe may actually be zero. If this is true, then the universe could, in principle, have arisen from nothing without violating the fundamental laws of physics. To understand this idea, we need to think about energy in a broader sense. Energy is not just the stuff we see as light, heat, or matter. It also includes gravitational energy, which behaves very differently from the forms of energy we're used to. Matter and radiation carry positive energy. They are things that add up, things that make the universe feel full. But gravity, unlike most forces, contributes negative energy. Whenever you pull two objects together with gravity, the system as a whole has less energy than the objects would have if they were infinitely apart. This is why it takes energy to separate objects against gravity, like lifting a rock off the ground. Here's the astonishing part. When cosmologists calculate the energy balance of the universe, they find that the positive energy of matter and radiation can, in theory, be exactly cancelled by the negative energy of gravity. Think of it like a cosmic accounting system. The stars, galaxies, and particles are entries on the credit side, while the gravitational attraction between them is a matching entry on the debit side. When you add everything up, the ledger balances at zero. This balance is not just an abstract idea, it has profound implications for the origin of the universe. If the total energy is zero, then the universe could have appeared spontaneously without needing an external deposit of energy. Nothing had to pay for the creation of the cosmos, because in the grand accounting, nothing was ultimately spent. The universe could simply emerge, with positive and negative energies balancing perfectly, leaving a net nothing behind the apparent something. Physicist Lawrence Krauss, among others, has popularized this concept by explaining that a universe from nothing is not only possible but perhaps inevitable. He points out that the mathematics of cosmology allows for a universe in which the energy required to create matter is exactly offset by the energy of gravity pulling everything inward. In that sense, creating a universe is like creating a perfectly balanced scale. Once in place, the balance requires no outside intervention. Stephen Hawking also leaned heavily on this idea. In his words, because there is a law such as gravity, the universe can and will create itself from nothing. What he meant is that if gravity inherently provides the counterweight to matter's positive energy, then no external agent is necessary to explain the existence of the cosmos. The universe can be self-contained, with the balance of energy acting as the mechanism that makes it possible. This concept is more than just theoretical speculation. When we look at the observable universe, we see hints that support this idea. For example, measurements of the universe's overall geometry and expansion rate suggest that it is remarkably close to flat in a mathematical sense. Flatness here refers to the balance of energy densities, precisely the kind of balance one would expect if the total energy of the universe is zero. In other words, the universe looks like it has been finely tuned to be energy neutral on the largest scales. Of course, this does not mean that the universe feels like nothing. From our perspective, stars burn, galaxies swirl, and energy flows everywhere. But beneath the surface, physics hints that this spectacular display is a grand illusion of imbalance. What we see as something may be perfectly counterbalanced by an invisible anti-something. Gravity's negative energy silently cancels out matter's positive energy, making the entire cosmic show possible without requiring an initial down payment. This idea also links back to the uncertainty principle we just discussed. If the energy of the universe adds up to zero, then there is no barrier to its spontaneous emergence. A quantum fluctuation does not need to produce an impossible surplus, it only needs to produce a perfectly balanced system of pluses and minuses. In this sense, the existence of the universe is not only permitted but might even be expected. The elegance of this picture is breathtaking. It transforms the question, how can something come from nothing, into how could nothing not give rise to something? If the rules of physics allow energy balances of zero, then the leap from nothingness to somethingness is not an unnatural violation but an inevitable unfolding. What we perceive as a universe brimming with matter and energy may simply be the visible face of a deeper symmetry, where positive and negative cancel out in a cosmic equation that always sums to zero. It is important, though, to recognize the subtlety here. Saying the universe has zero total energy does not mean there is literally nothing in it. There are still stars, galaxies, and people asking questions. What it means is that the cost of this richness is offset elsewhere in the fabric of reality. Just as a mountain and a valley form together, the peak is matched by the depth, so too the universe may be matched by its own invisible counterbalance. Together, they form a complete whole that requires nothing external to explain its existence. In this view, the universe is not a violation of nothingness but its perfect expression. What we call something is simply the positive face of an equation whose negative side is hidden in the pull of gravity. Existence itself may be a zero-sum game, and that is precisely why it can exist at all. One of the most extraordinary ideas in modern cosmology is the theory of cosmic inflation, the notion that our vast universe, with its billions of galaxies and unimaginable expanses of space, might have begun as a minuscule fluctuation that expanded at an almost inconceivable rate in the tiniest fraction of a second. Inflation is not just a wild speculation, it is a powerful framework that helps explain some of the deepest puzzles about why the universe looks the way it does. And at its core lies the astonishing claim that something unimaginably small could blow up into everything we see around us today. To appreciate inflation, let's first recall what the early universe was thought to be like. For much of the 20th century, cosmologists assumed that the Big Bang was a kind of simple explosion, an expansion of hot, dense matter and energy that eventually cooled to form stars and galaxies. But as they studied the universe more closely, troubling questions emerged. Why is the universe so uniform in all directions, with the cosmic microwave background radiation nearly the same temperature everywhere? Why is the geometry of space so close to perfectly flat, as if finely balanced on a knife's edge? Why don't we see huge amounts of magnetic monopoles or other exotic relics that particle physics predicts should have been produced in the early universe? In the late 1970s and early 1980s, physicists like Alan Guth, Andre Linde, and others proposed inflation as an answer. The basic idea is elegant. In the very first fraction of a second after the universe came into being, about 10 cubed seconds to 10 cubed squared seconds, space itself underwent an exponential expansion, inflating far faster than the speed of light. This does not violate relativity, because it is not matter moving through space faster than light, but space itself expanding. In this blink of cosmic time, a region smaller than a subatomic particle could balloon to a size larger than the observable universe today. What could drive such a dramatic expansion? The culprit is thought to be a special kind of energy locked into a quantum field, sometimes called the inflaton field. In a high-energy state, this field would have acted like a repulsive form of gravity, pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its stored energy converted into particles and radiation, filling the universe with the ingredients for stars, galaxies, and ultimately, life. The universe then transitioned smoothly into the hot, dense state that we traditionally associate with the Big Bang. In this sense, inflation can be thought of as the spark that ignited the Big Bang itself. What makes inflation so compelling is how well it explains the universe we observe. The remarkable smoothness of the cosmic microwave background, the faint afterglow of the Big Bang, is no longer a mystery under inflation. Regions of space that look identical today were once close enough to share information before inflation blew them apart, ironing out any irregularities. Inflation also explains why the universe is so flat. Any initial curvature, no matter how pronounced, would have been stretched to near perfection by the runaway expansion, just as the surface of a balloon looks flatter the more you inflate it. Even more fascinating is how inflation turns quantum fluctuations into the seeds of cosmic structure. Remember those tiny jitters in the quantum vacuum we discussed earlier? During inflation, these microscopic fluctuations were stretched to astronomical scales. Places where the fluctuation added a little extra energy became slightly denser regions, while places with less energy became slightly emptier. Over billions of years, gravity amplified those tiny variations, pulling matter together to form galaxies, stars, and planets. If inflation is correct, then every galaxy in the night sky owes its existence to the restless bubbling of the quantum vacuum in the universe's first split second. It is almost mind-bending to realize that the vast cosmic web of galaxies we see today, the great filaments and clusters stretching across billions of light-years, may be nothing more than magnified quantum noise. The largest structures in the universe are, in this sense, fossils of the smallest fluctuations imaginable. Inflation is the bridge between the quantum world and the cosmic scale, showing how the tiniest uncertainty can blossom into everything. Of course, inflation raises deep questions of its own. What exactly is the inflaton field, and why did it exist? Did inflation happen once, or could it be eternal, spawning countless bubble universes, each with different properties? Some versions of inflation suggest that our universe may be just one of many in a grand multiverse, each arising from inflationary bursts in an endlessly inflating background. This means that our something may not be unique, but one possibility among countless others. But whether or not the multiverse is real, inflation remains one of the most powerful ideas in physics. It takes the puzzle of how a universe can come from nothing and provides a natural mechanism. A tiny fluctuation, permitted by the uncertainty principle and balanced by gravitational energy, can inflate into a universe like ours in the blink of an eye. No external trigger is required, no hand from outside the cosmos pushing it along. The laws of physics themselves may have carried the potential for creation, with inflation as their dramatic expression. When you think about it, this is both humbling and exhilarating. The vast universe that feels so ancient and immovable may have sprung from a quantum tremor smaller than an atom. Every star in the sky, every planet, every moment of human history, all of it may trace back to a fraction of a second when a tiny fluctuation swelled into everything. Inflation suggests that our existence is not just possible but perhaps inevitable, given the restless nature of nothingness and the strange creativity of the vacuum. When people hear the phrase Big Bang, it often conjures an image of a fireball exploding in the middle of pre-existing emptiness, like a cosmic bomb that went off in some vast, silent void. But this picture, while vivid, is profoundly misleading. The Big Bang was not an explosion in space, it was the sudden expansion and creation of space-time itself. This distinction is crucial if we want to understand how matter, energy, and even the very fabric of reality could emerge from what we casually call nothing. Let's unpack this carefully. In an ordinary explosion, there is a background in which the explosion occurs: a room, a battlefield, the vacuum of outer space. The debris from the explosion expands outward, rushing into that pre-existing environment. But in the Big Bang, there was no space or time outside into which the universe could expand. Space-time itself came into being at that moment. To ask what the universe expanded into is like asking what lies north of the North Pole. The question assumes a framework that does not exist. This means that before the Big Bang, there was no where and no when. Time itself begins with the Big Bang. That's an unsettling thought, because it strips away our intuitive sense of causality. We normally think in terms of cause and effect, one thing happening before another in time. But if time itself begins at the Big Bang, then there was no before in the conventional sense. The question of what happened before the Big Bang may therefore be meaningless, or it may require a radically different way of thinking about reality. What did the Big Bang actually look like? Cosmologists describe it not as a point of matter exploding outward, but as the uniform expansion of space itself from an initial hot, dense state. Imagine the surface of a balloon being inflated. The balloon's surface represents space, and as the balloon expands, every point on the surface moves away from every other point. There's no privileged center of the expansion. The expansion happens everywhere at once. Now, push this analogy further. Unlike a balloon, the universe has no external space into which it expands. The expansion is not into something, it is the stretching of space itself. This view resolves one of the greatest misconceptions about the Big Bang, that it was an event that happened somewhere. In reality, it happened everywhere, because everywhere was the universe. The very coordinates of space and time, what we use to define here and now, were born in that singular moment. If the Big Bang had not occurred, there would be no place for it to occur in, and no time in which it could have happened. It is not just the contents of the universe that came into being, but the stage on which they play out. This is why some physicists argue that the Big Bang represents not just the beginning of matter and energy, but the emergence of the laws of physics themselves. Space-time is not a passive backdrop. It is woven into the structure of reality, governed by Einstein's equations of general relativity. When space-time itself came into being, it carried with it the fundamental rules that would shape the unfolding cosmos: the nature of gravity, the behavior of light, the quantum fluctuations that seeded galaxies. The laws of physics are not outside the universe, imposing order, they are part of what was born in the Big Bang. So when we contrast the Big Bang with nothing, we must be precise about what we mean by nothing. If by nothing we mean the absence of space, time, matter, and energy, then the Big Bang was not an event occurring within nothing, it was the transformation of nothing into something. If by nothing we mean the quantum vacuum, with its restless fluctuations, then the Big Bang can be seen as one of those fluctuations magnified on a cosmic scale. In either case, the Big Bang challenges the very distinction between nothing and something. Another key point is that the Big Bang was not a single moment in time that we can locate and say, here is when it all started. Instead, it is the boundary of time itself. When cosmologists extrapolate backward using Einstein's equations, they find that the density and temperature of the universe increase without bound as you approach time zero. But this singularity is not a literal physical object. It's a signal that our current theories break down. It marks the edge of what general relativity can describe. Beyond that, we need quantum gravity, a theory that does not yet fully exist, to tell us what nothing really means and how it became something. Even so, what we do know paints an awe-inspiring picture. The Big Bang was the moment when the fabric of existence unfurled. The universe did not expand into emptiness. Emptiness itself was created in the expansion. The flow of time did not measure an ongoing process. It began ticking with that process. The stage, the actors, and the script all appeared together. And from that primordial instant, 13.8 billion years ago, the universe has been evolving, cooling, and structuring itself into the galaxies, stars, planets, and conscious beings who can now look back and ask, how did it all begin? It is humbling to realize that when we peer deep into space with our telescopes, we are not just looking at distant galaxies, we are looking back in time, toward the moment when space and time themselves erupted into being. We are seeing echoes of the Big Bang in the faint glow of the cosmic microwave background, the afterglow of creation. Every photon of that ancient light carries with it the story of how the universe transitioned from nothing to something. In this way, the Big Bang is not merely a scientific model. It is a profound statement about existence itself, that reality did not require a stage on which to appear, because the stage and the play were born together. The Big Bang was not an explosion of matter into space, it was the birth of space-time itself, carrying matter and energy along with it. And in that distinction lies the key to why the universe exists at all. Stephen Hawking, perhaps the most iconic physicist of our time, dared to confront one of the deepest and most unsettling questions humans can ask. Does the universe need a cause outside of itself to exist, or can it simply be? His answer, grounded in the union of quantum mechanics and general relativity, was bold and unsettling to traditional intuition. He proposed that the universe might be self-contained, that it could arise spontaneously, governed entirely by the laws of physics, without requiring any external trigger, creator, or cause. To understand Hawking's insight, we need to recall how physics traditionally approached beginnings. In classical cosmology, the Big Bang was seen as a singularity, a point of infinite density and temperature, where the laws of physics break down. At this singularity, time itself seems to come to a halt, and beyond it, our equations cannot describe what came before. This looked, to many, like a place where science reached its limits and perhaps required metaphysics, philosophy, or theology to step in. But Hawking, working with James Hartle in the 1980s, proposed a radical alternative. What if the universe has no singular beginning in the usual sense? They developed what is known as the no-boundary proposal, which suggests that time itself may be finite but without a boundary, like the surface of a sphere. On Earth, you can travel north until you reach the North Pole, but there is no point further north than that. The end is not a boundary but a smooth cap. Similarly, in Hawking's view, time may curve back on itself in the earliest stages of the universe. The universe would thus be finite in duration but without a sharp edge, without a point at which one must ask, what came before? This insight reframes the question of origins. If the universe has no boundary in time, then the need for an external cause disappears. The universe simply exists as a self-contained system. Its laws are enough to explain its own emergence. In this sense, asking what caused the Big Bang becomes meaningless, much like asking what's north of the North Pole. In his later works, especially in the Grand Design co-authored with Leonard Mlodinow, Hawking took this line of reasoning even further. He argued that because the law of gravity exists, the universe can and will create itself from nothing. This was not a dismissal of mystery, but an embrace of the strange implications of modern physics. The laws of quantum mechanics allow for spontaneous fluctuations, and when coupled with gravity's peculiar negative energy, the creation of a universe is not forbidden but natural. The laws themselves are sufficient to bring about the cosmos. No outside agent is required to light the fuse. This vision was controversial. Critics asked, if the universe relies on laws of physics to exist, then where did those laws come from? Are they not themselves something rather than nothing? Hawking's defenders countered that the laws of physics may not be things that exist in the ordinary sense. Instead, they may be descriptive statements about what is possible, abstract patterns inherent in reality itself. In this view, mathematics and physics are not imposed from outside but are the fabric of reality. The universe does not need an architect, it is built from the logic of its own laws. What made Hawking's perspective so powerful was not only its philosophical boldness but also its connection to concrete physics. His work on black holes revealed that space and time are not absolute, eternal backdrops but dynamic, flexible entities that can warp, curve, and even evaporate. If space-time itself can emerge, change, and vanish within our universe, why should it not also emerge spontaneously as a whole? In other words, if the physics of black holes shows us that beginnings and endings are not absolute, then perhaps the universe as a whole can exist without needing an external starting gun. To many, Hawking's self-contained universe is unsettling because it removes the comforting notion of an ultimate cause. But it is also profoundly liberating. It suggests that the cosmos is not something precarious, hanging on the will of something outside, but something stable and inevitable, arising from the nature of reality itself. In Hawking's words, what is it that breathes fire into the equations and makes a universe for them to describe? His answer was that nothing external is needed. The fire is already within the equations. This does not mean the mystery is gone. Even if the universe is self-contained, we are left to wonder why the laws of physics are the way they are, why there is a structure at all rather than chaos, and why mathematics describes reality with such precision. Hawking himself admitted that science might never answer the ultimate why questions. But he insisted that the how of existence, how something can arise from nothing, was within the reach of physics. The no-boundary universe and the self-sufficiency of natural law represent his most enduring attempt to show that. In the end, Hawking's insight is as much a philosophical statement as a scientific one. Perhaps the universe does not need a cause. Perhaps existence is not a miracle in need of explanation from beyond, but the natural unfolding of laws that leave no room and no necessity for anything outside themselves. The universe may not be a creation in the traditional sense, it may simply be. John Archibald Wheeler, one of the most imaginative minds in 20th century physics, was never afraid to ask unsettling questions that blurred the line between physics and philosophy. He contributed enormously to concrete science. He helped coin the term black hole, advanced our understanding of quantum mechanics, and mentored generations of physicists. Yet Wheeler also spent much of his career probing questions that many considered too speculative. Where do the laws of physics themselves come from? Are they eternal truths written into the fabric of reality, or could they have emerged from something deeper, perhaps even from chaos or randomness? This line of thought gave rise to his provocative phrase, law without law. At its heart, this idea challenges the assumption that the laws of physics are fixed, immutable, and timeless. Instead, Wheeler suggested that what we call the laws of nature may be emergent patterns, the stable regularities that rise out of an underlying realm of unpredictability. To grasp the audacity of this idea, think about how we normally understand science. Physics is built on the premise that there are fundamental laws, like gravity, electromagnetism, and quantum mechanics, that govern everything. These laws are often seen as timeless, existing independently of the universe they describe. But Wheeler asked, what if that's the wrong picture? What if the laws are not the starting point but the outcome of the universe's unfolding? In other words, what if the universe began in a state of raw chaos, with no fixed rules, and through a kind of natural selection of possibilities, the stable regularities we now call laws crystallized? An analogy might help. Consider a chaotic stream of water rushing down a mountainside. At first, the flow seems random, full of turbulence and unpredictability. But if you watch closely, certain patterns begin to emerge: swirling eddies, repeating ripples, stable currents. These patterns are not imposed from outside, they arise naturally from the chaos itself. Wheeler imagined something similar at the birth of the universe. From a primordial state of randomness, stable structures of behavior could have emerged, solidifying into what we perceive as the laws of physics. This idea resonates with developments in modern science. In statistical mechanics, order can emerge from disorder when large numbers of particles interact. In complexity theory, we see how systems as diverse as ecosystems, markets, and brains develop regular patterns from countless unpredictable interactions. Could the laws of physics themselves be the ultimate example of emergence? Wheeler's law without law also connects to the idea of the participatory universe, another of his radical proposals. He suggested that the act of observation in quantum mechanics, the fact that measurement seems to play a role in shaping outcomes, might mean that the universe's very structure emerges in response to participation by observers. In this sense, the laws are not preordained but co-created, taking shape through a dialogue between the raw potential of the universe and the process of observation. If laws can emerge, then they may not be unique. Perhaps in other possible universes, different patterns crystallized out of the chaos, producing different laws. This ties naturally into the multiverse hypothesis, where each universe could have its own set of emergent laws, depending on the initial randomness and the way patterns stabilized. Our universe may feel lawful because we inhabit one of those stable patterns, not because laws are timeless truths written in stone. The concept of law without law also reframes the question of nothing. If the laws of physics are not eternal but emergent, then the idea of creation from nothing becomes less mysterious. Instead of asking, how did something obeying fixed laws arise from nothing? We might ask, how did order arise from disorder? That question feels more natural, because we see examples of it around us all the time. Snowflakes forming from vapor, life emerging from chemistry, structure arising in turbulent flows. Perhaps the universe itself is the ultimate example of order crystallizing out of chaos. Of course, Wheeler's suggestion remains speculative. It is not yet clear how to formalize a theory where laws emerge from lawlessness, or how such an idea could be tested. But it points to an important humility in our understanding. We tend to assume that the laws of physics are the foundation of reality. Wheeler invites us to flip the picture. Maybe the universe itself is the foundation, and the laws are just the patterns it has settled into over time. This notion is dizzying because it undermines our sense of certainty. If the laws are emergent, then they are not ultimate. They may be contingent, temporary, or even different in other regions of existence. And yet, there is also a profound beauty in this idea. It suggests that order is not imposed but discovered, that the universe is not a machine obeying rigid instructions but a self-organizing system whose very rules grew out of possibility and chaos. In Wheeler's poetic vision, the universe is not governed by law so much as it gives birth to law. And if this is true, then asking how matter arose from nothing is not the whole question. We must also ask how the laws that allowed matter to arise themselves emerged. Law without law is Wheeler's invitation to imagine a universe where not only matter and energy, but even the principles that govern them, are products of an unfolding cosmic creativity. At the very beginning of the universe, in those unimaginably tiny fractions of a second after the Big Bang, physicists believe reality was in a state of extraordinary elegance and simplicity. The forces of nature, the ones we now distinguish as gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may not have been separate at all. Instead, they might have been unified in a single, perfect symmetry. All the particles and forces were intertwined, indistinguishable from one another, existing in a kind of harmonious balance. But that symmetry did not last. As the universe expanded and cooled, that perfect balance shattered, a process known as symmetry breaking. And it is precisely in this breaking that the richness of our universe, its particles, its forces, its structures, came into being. To understand this, let's first reflect on what symmetry means in physics. Symmetry is not just about shapes and patterns, like a snowflake or a butterfly's wings. In physics, symmetry refers to the invariance of a system under certain transformations. For example, if you rotate a circle, it still looks the same. That's rotational symmetry. In the early universe, the laws of physics may have exhibited a much deeper symmetry, a set of transformations under which all particles and forces were equivalent. Everything was in balance. But here's the catch. Perfect symmetry does not always lead to complexity. If the universe had remained in that pristine state, perhaps nothing interesting would have emerged. It is in the breaking of symmetry that diversity arises. Think about water freezing into ice. Above 0 degrees Celsius, water molecules move freely, and the liquid is uniform, symmetrical in every direction. But as the temperature drops, the symmetry breaks. The molecules lock into a rigid lattice, forming crystals with definite orientations. That breaking of symmetry produces structure. Similarly, when the early universe cooled below certain thresholds, its fundamental symmetries fractured, and out of those fractures came the distinct forces and particles we know today. One of the first great symmetry breakings is thought to have occurred when the strong nuclear force split away from the other forces. Later, the electroweak force, which unified electromagnetism and the weak nuclear force, underwent its own breaking, leaving electromagnetism and the weak force as distinct. At each stage, the universe lost some of its original elegance, but it gained structure, complexity, and the potential for new forms of matter. A simple analogy is a ball balanced on the very top of a perfectly symmetrical hill. At the peak, all directions are equivalent. But the ball cannot stay there forever. The slightest nudge will send it rolling down one side. Once it rolls, the symmetry is broken. It chooses one path among many. In the early universe, the ball was the state of reality itself, perched in perfect balance. As the universe expanded and cooled, the balance tipped, and reality chose particular configurations. Forces split apart. Particles gained distinct identities. The symmetry broke, and the universe rolled into the valleys of possibility. This breaking is not random chaos. It follows the underlying mathematical structure of physics. The symmetries still exist in the equations, but they are hidden, much like the symmetry of a cube is hidden when it melts into water. The universe, in this sense, still carries the ghost of its original perfection, but that perfection is disguised by the broken patterns we observe. The consequences of symmetry breaking were profound. Without it, particles would not have gained their distinct properties. Forces would not have specialized to allow atoms, chemistry, stars, and galaxies to form. The very fact that we have matter at all, matter that can clump, form structures, and eventually give rise to life, depends on those primordial moments when perfect balance gave way to asymmetry. What's even more fascinating is that symmetry breaking helps explain why the universe seems to have direction and diversity. If everything had stayed symmetrical, perhaps matter and antimatter would have annihilated in perfect balance, leaving nothing. But with broken symmetry, small imbalances became magnified, allowing matter to dominate just enough for the universe we inhabit to exist. The breaking of symmetry was not a flaw. It was the very mechanism that made existence possible. Modern physics continues to explore the details of these transitions. Particle accelerators like the Large Hadron Collider attempt to recreate conditions similar to those in the early universe, to study how symmetries break and what particles emerge. The discovery of the Higgs boson in 2012 was a major step, because the Higgs field is intimately tied to one of the most important episodes of symmetry breaking. It is through interaction with the Higgs field that particles gained mass, distinguishing themselves from massless radiation. The story of symmetry breaking is a story of creation through imperfection. Out of an initial unity came diversity. Out of balance came structure. And out of the shattering of primordial symmetry came the possibility of everything we see around us: galaxies, stars, planets, life, and minds capable of asking how it all began. In the universe's earliest moments, perfection was sacrificed. But in that sacrifice, the cosmos found the richness that makes it what it is. When we look around the universe, one of the most basic features of matter seems obvious. Things have mass. From the tiniest speck of dust to the most massive star, every piece of matter resists being pushed around, has weight in a gravitational field, and carries inertia. But from the standpoint of fundamental physics, this is not obvious at all. In fact, if you strip down the equations of particle physics to their simplest form, the fundamental particles, like electrons, quarks, and neutrinos, ought to be massless, zipping around at the speed of light. Yet clearly, they aren't. They have mass, and without that mass, atoms would never form, chemistry would never exist, and the universe as we know it would be impossible. So the question arises, where does mass come from? The answer lies in something that permeates the universe, an invisible presence known as the Higgs field. Think of it not as a particle floating around in space, but as a kind of universal medium, filling every corner of the cosmos. Just as air fills a room, the Higgs field fills the vacuum. It is not something that can be turned off or confined. It is built into the structure of reality itself. Here's how it works. Imagine trying to walk across a crowded room at a party. If no one is there, you move effortlessly, quickly, with no resistance. That's what it would be. Like for particles in a universe without the Higgs field, they would be massless, flying through space at light speed, unable to slow down or clump together. But now imagine the room is filled with people, and as you try to move, others keep interacting with you, grabbing your arm, slowing you down, impeding your motion. Suddenly, you feel heavy, resistant to being pushed. That is the effect of the Higgs field on particles. As they move through this invisible medium, their interactions with it give them inertia, which we interpret as mass. Not all particles interact with the Higgs field equally. Some, like the top quark, couple very strongly to it and thus become very massive. Others, like the electron, interact only lightly, gaining just a small amount of mass. And intriguingly, some particles, like the photon, the particle of light, do not interact with the Higgs field at all, which is why they remain massless and always travel at the speed of light. This difference in interaction explains why the universe contains such a diversity of particle masses. Now, the Higgs field isn't just an abstract idea. It has a particle associated with it, known as the Higgs boson. This particle is like a ripple in the field, much as a photon is a ripple in the electromagnetic field. For decades, physicists suspected the Higgs boson must exist, because without it, the standard model of particle physics, the incredibly successful framework that explains almost everything we know about particles and forces, would fall apart. But the Higgs boson was elusive. It required enormous amounts of energy to create, energies far beyond what previous accelerators could reach. That's why the construction of the Large Hadron Collider, LHC, at CERN was such a monumental project. This machine, buried beneath the French-Swiss border, accelerates protons close to the speed of light and smashes them together, recreating conditions similar to those a trillionth of a second after the Big Bang. In 2012, after years of painstaking work, the LHC experiments finally confirmed the existence of the Higgs boson. It was a triumph not just for physics but for human curiosity itself. An invisible field that permeates the universe had left its fingerprint in the form of a particle that we could detect. But the Higgs is more than just a missing piece in a puzzle. It is central to the story of how something emerged from nothing. In the early universe, before symmetry breaking, particles had no mass. They were all behaving like massless radiation, unable to bind into stable structures. But when the Higgs field turned on as the universe cooled, particles suddenly acquired mass. That moment was like the universe drawing a line between light and matter, between energy that could spread infinitely and stuff that could clump together. With mass came the ability to form protons, neutrons, atoms, molecules, stars, and eventually living beings. Without the Higgs field, there would be no things at all, just endless, weightless radiation rushing through an empty void. What's even more fascinating is that the Higgs field shows us how deeply hidden layers of reality can be. For billions of years, the Higgs field quietly shaped the universe without anyone knowing it existed. Only by smashing particles at the highest energies humans could engineer did we finally glimpse it. That discovery reminds us that much of the universe's most important machinery is invisible, not just because it is hidden from view, but because it operates at a level so fundamental we barely notice it. Yet, the Higgs discovery also raises new mysteries. Why does the Higgs field have the particular strength that it does? If it were slightly weaker, particles would be almost massless, and atoms would not form. If it were stronger, particles would be so heavy that complex structures would be impossible. The fact that its value is finely tuned to allow a life-permitting universe is one of the great puzzles of modern physics. Some suggest this might be explained by the multiverse idea, where many universes exist with different values, and we happen to live in one where the Higgs field allows stability. Others hope for a deeper principle that fixes the value precisely. In any case, the Higgs field is not just a technical detail of particle physics, it is one of the linchpins of existence. It transformed a massless, featureless early universe into a rich and structured cosmos. It turned energy into matter, radiation into resistance, nothingness into somethingness. And in a way, every stone, star, and person carries the imprint of that field, for it is the reason we have weight, substance, and presence at all. Among all the questions humans have ever asked, One towers above the rest in both simplicity and depth. Why is there something rather than nothing? It sounds almost childlike, the kind of question that might emerge in a moment of innocent wonder, but it is also one of the most profound puzzles ever conceived. It cuts deeper than any question of how the universe works, because it does not just ask about the rules of reality, it asks why reality exists at all. Consider the possibility of nothing. Not empty space, not a vacuum, not even time ticking quietly away in a dark void. True, absolute nothing. No laws of physics, no particles, no fields, no mathematics, no potential. Just pure non-existence. That scenario feels intuitively possible. After all, if nothing truly means the absence of everything, then it requires no explanation. Non-existence does not need a cause. Yet, here we are, living beings in a vast universe filled with galaxies, stars, and planets. Reality exists, and that fact is astonishing, because it means existence triumphed over non-existence. Why? Why should something exist rather than nothing? Philosophers have wrestled with this question for centuries. Some argue that nothingness is unstable, that existence is more natural than non-existence. Others counter that non-existence is simpler and therefore more likely, making the existence of a universe a great mystery that demands an explanation. Still others suggest that the question itself may be ill-posed, that once we think carefully about what nothing really means, we realize that true nothingness may be impossible. Science approaches this puzzle differently. Instead of asking why is there something, in an abstract sense, physics tries to show how something could naturally arise from what appears to be nothing. As we have seen, the quantum vacuum is not empty but teeming with fluctuations. In that view, nothing may never truly exist in the strict philosophical sense. What we call nothing may actually be a state of potential, a fertile emptiness from which particles and universes can emerge. If that is the case, then the question becomes not why something, but why this particular something? Why this universe with these laws, these constants, this structure? Still, even the most sophisticated physics can only go so far. Suppose we describe in exquisite detail how the universe arose from quantum fluctuations, symmetry breaking, cosmic inflation, and the unfolding of the Higgs field. We may still be left with the deeper question: why are there quantum laws at all? Why does mathematics exist? Why is there a framework that allows anything to arise? Physics can show us the mechanics of how something emerges, but the leap from absolute nothing to the possibility of something seems to demand more than mechanics. Some philosophers and scientists suggest that existence might be necessary. That is, maybe the existence of something, whether physical, mathematical, or logical, is unavoidable. In this view, nothingness is not a real option. Just as the number zero exists in mathematics whether we like it or not, perhaps the framework of existence itself is eternal and inevitable. If so, then asking why is there something is like asking why is 2 plus 2 is equal to 4. The answer is that it simply could not be otherwise. Others argue that chance might be the ultimate explanation. Perhaps the laws of physics popped into existence randomly, and with them, the universe itself. If multiple universes are possible, then the fact that we exist in one is not surprising. After all, only a universe that exists could ask the question in the first place. This is sometimes called the anthropic principle. The universe must allow for observers, otherwise no one would be here to wonder about it. From this perspective, the fact that there is something is not mysterious. It is simply the case that only something can host beings like us. But these answers, while thought-provoking, may not satisfy the deep itch behind the question. To ask why there is something instead of nothing is to reach for an ultimate explanation, one that may forever evade the tools of science. It forces us to confront the limits of human understanding. Can the human mind, born from a small planet in an ordinary galaxy, ever hope to grasp why existence itself exists? Or is this question destined to remain a mystery, a reminder that the universe is not obliged to reveal all of its secrets to us? And yet, perhaps the wonder lies not in finding a final answer but in the fact that the question itself can be asked. We live in a universe where minds exist, where consciousness can reflect on its own origins, where atoms that were once forged in the heart of stars have come together to form beings who stare into the night sky and ask, why is there something rather than nothing? It is here, in this moment of wonder, that philosophy and science meet. Science can give us the mechanisms, the processes, the equations. Philosophy can give us frameworks to think about the ultimate why. But together, they remind us that the very existence of something, anything at all, is not just a trivial fact. It is the greatest mystery. In the earliest instance of the universe, when everything was unimaginably hot and dense, matter and antimatter were born together in equal measure. At least, that's what our best understanding of physics suggests. For every electron, there was a positron. For every proton, an antiproton. For every quark, an antiquark. In theory, they should have perfectly balanced one another, like black and white squares on a chessboard. And here's the catch: when matter and antimatter meet, they annihilate, disappearing in a flash of pure energy. If the early universe had truly contained equal amounts, everything should have cancelled out. The cosmos should have been left as nothing more than a sea of radiation, empty of stars, planets, and life. But clearly, that isn't the case. Look around you. Everything you see, your body, the planet beneath your feet, the stars overhead, is made of matter. Antimatter, by contrast, is vanishingly rare in our universe. So somewhere in those first few fractions of a second, a subtle imbalance tipped the scales. For every billion pairs of matter and antimatter particles that annihilated, there was just one extra particle of matter left behind. It was a tiny excess, a 1 in a billion preference, but it was enough. Those survivors became the raw material for everything we now see in the cosmos. This puzzle, why matter won over antimatter, is known as the problem of baryon asymmetry. And it is one of the great mysteries of physics. The laws of nature, as we understand them, seem to treat matter and antimatter almost identically. They are mirror images, same mass, opposite charge. Their interactions appear symmetrical. So why should the universe have favored one over the other? The answer may lie in subtle asymmetries hidden within the laws of physics themselves. In the mid-20th century, scientists discovered that certain kinds of particle interactions do not preserve perfect symmetry. This is called CP violation, where C stands for charge, swapping particles for antiparticles, and P stands for parity, flipping spatial orientation, like a mirror reflection. In some rare processes, nature does not treat matter and antimatter exactly the same. These tiny differences could, under the extreme conditions of the early universe, have produced that slight excess of matter over antimatter. One key area of research into this imbalance involves the behavior of quarks, the fundamental building blocks of protons and neutrons. Experiments with particles called kaons and B-mesons have shown CP violation in action, revealing that matter and antimatter don't always behave as perfect twins. But the amount of CP violation observed so far in these experiments is not enough to explain the huge dominance of matter in the universe today. That means there must be more going on, hidden mechanisms, undiscovered physics, or deeper principles that we have yet to uncover. Another candidate in this puzzle is the neutrino, one of the strangest and most ghostly particles in physics. Neutrinos barely interact with matter, yet they may have played a crucial role in tilting the cosmic balance. If neutrinos and their antiparticles behaved differently in the early universe, that could have helped generate the excess matter we depend on. This idea, known as leptogenesis, is an active area of theoretical research. What makes this question so profound is its connection to our very existence. If the universe had not favored matter ever so slightly, there would be no galaxies, no stars, no planets, no life. The entire cosmos would have been reduced to a cold bath of photons, forever empty. That 1 in a billion imbalance is the reason we are here to ponder it. The universe's bias toward matter is not just a quirk of physics, it is the foundation of our existence. Experiments continue to probe this mystery. Facilities like CERN and neutrino observatories buried deep underground are searching for hints of how matter and antimatter differ. The stakes are high, because solving this puzzle could reveal new layers of physics beyond the standard model, possibly even connecting to grander theories that unify forces or describe the earliest instance after the Big Bang. There's also a poetic irony here. Antimatter isn't gone entirely. We can create it in particle accelerators, and tiny amounts are produced in cosmic ray collisions and radioactive decay. When antimatter meets matter today, the annihilation releases energy just as it did in the early universe. In fact, Antimatter is so powerful that science fiction often imagines it as the ultimate fuel. But in reality, its rarity reminds us of how precarious our existence is. A universe with a slightly different balance sheet might never have allowed stars to shine or atoms to form. So the dominance of matter over antimatter is not just a technical detail, it is one of the most decisive turning points in cosmic history. It tells us that the universe is not perfectly symmetrical, that some subtle preference nudged reality toward existence rather than emptiness. Without that preference, we would not be here. And the fact that we don't yet know exactly why matter makes this question one of the most haunting in science. It sits at the intersection of physics, philosophy, and wonder. The story of how a tiny asymmetry in the fabric of creation determined the difference between a universe filled with life and a universe that remained forever barren. The notion of a multiverse, the idea that our universe might be just one among countless others, is one of the most daring and controversial ideas in modern science. For some, it sounds like pure science fiction, a desperate attempt to explain the inexplicable. For others, it is a natural consequence of the very physics we already accept, an unavoidable extension of our theories. And when it comes to the question of how matter could come from nothing, the multiverse provides a strikingly bold possibility. Maybe our universe is not unique, and maybe nothing is never really nothing, but rather a bubbling sea of potential universes constantly coming into being. Let's begin with the intuition behind this idea. When physicists study the laws of nature, they find that many of the constants and parameters that shape our world, things like the strength of gravity, the charge of the electron, or the value of the Higgs field, seem finely tuned for life and structure. If gravity were slightly stronger, stars might collapse too quickly. If weaker, galaxies might never form. If the electromagnetic force were different, atoms might not bind. The odds of all these constants lining up to allow a universe with complexity seem, at first glance, astronomically small. One way to address this mystery is to suggest that our universe is just one of many, perhaps an infinite collection of universes, each with different laws, constants, and conditions. In such a multiverse, most universes would be barren, sterile, or chaotic. But some, by chance, would have the right properties to allow galaxies, stars, planets, and life. We find ourselves in one of those universes not because it was specially designed, but simply because only in such a universe could beings like us exist to wonder about it. This reasoning is often connected to what is called the anthropic principle. There are several scientific pathways that lead naturally to a multiverse idea. One comes from cosmic inflation, the theory that the universe underwent a brief period of exponential expansion in its earliest moments. In many versions of inflation, this process doesn't stop everywhere at once. Instead, it keeps going in some regions, creating a vast cosmic foam of bubble universes. Each bubble may have its own laws of physics, its own version of space and time. Our observable universe would be just one bubble among countless others. Another pathway comes from string theory, a leading candidate for a theory of everything. String theory allows for an enormous number of possible solutions, different ways to compactify extra dimensions and different configurations of fields. Each solution corresponds to a different possible universe, with different values for the fundamental constants. The sheer number of possibilities, sometimes estimated at around 10 to the power of 500, suggests that if a multiverse exists, it could contain an unfathomable variety of universes, each with its own version of something emerging from nothing. Quantum mechanics also hints at a multiverse through the many-worlds interpretation. In this view, every quantum event with multiple possible outcomes does not choose just one path but branches into many, creating parallel realities. Every decision, every particle interaction, every quantum fluctuation spawns new universes. From this perspective, our universe is just one branch among infinitely many, all equally real. What does this mean for the question of how matter arose from nothing? In a multiverse, the creation of universes could be a natural and ongoing process. What looks like nothing might actually be a fertile background, a quantum foam or a higher dimensional reality, where new universes continually bud off. Each universe starts with its own version of laws, energy, and matter. Our universe, then, is not a unique miracle but one expression of a much broader cosmic reality. Of course, the multiverse idea is not without controversy. Critics argue that it risks moving beyond science into metaphysics, because other universes may be forever beyond our observational reach. How can we test the existence of realms we cannot access? Some physicists worry that invoking the multiverse to explain fine-tuning is like giving up the search for a deeper, more fundamental explanation. Others, however, point out that even if we cannot see other universes directly, we might still find indirect evidence, such as subtle imprints left on the cosmic microwave background, or predictions from inflation and string theory that can be tested within our own universe. Whether real or not, the multiverse transforms the question of something from nothing. If there are infinitely many universes, then existence itself might be the rule, not the exception. Nothing may never truly exist. Instead, there may always be a larger backdrop of reality giving rise to new universes. From this perspective, our universe's emergence from apparent nothingness is not a singular event but part of an eternal, unending process. And perhaps the most humbling aspect of the multiverse idea is what it says about our place in the cosmos. For centuries, humanity has repeatedly discovered that we are not at the center of things. Not the center of the Earth, not the center of the solar system, not the center of the galaxy. The multiverse would be the ultimate extension of that lesson. Not only is our planet not special, and our galaxy not unique, our entire universe may be just one of countless others, a small ripple in an endless cosmic ocean. Quantum cosmology is one of the boldest intellectual frontiers ever attempted by humanity. It asks a question that, at first glance, seems almost paradoxical. If quantum mechanics governs the tiniest particles in the universe, could it also govern the universe as a whole? And if so, what does that mean for the origin of everything, the leap from nothing to something? This field attempts to blend the two great pillars of modern physics: quantum theory, which excels at describing the subatomic world, and general relativity, which describes the vast architecture of space and time. The challenge is immense, because these two frameworks, though wildly successful in their domains, resist easy unification. Yet without such unification, our understanding of the earliest moments of the universe remains incomplete. To appreciate what quantum cosmology is trying to do, consider first what quantum mechanics tells us about particles. At the smallest scales, particles do not behave like tiny billiard balls but as fuzzy clouds of probability. They can exist in superpositions, meaning they are in multiple states at once until measured. They can tunnel through barriers that seem impossible to cross. They can pop in and out of existence briefly, borrowing energy from the vacuum under the rules of the uncertainty principle. All of these phenomena seem strange, but they have been confirmed in countless experiments, from electron interference patterns to quantum entanglement. Now, imagine extending these principles not just to individual particles, but to the entire universe. If quantum rules apply everywhere, then the universe itself should be describable as a quantum object. In this view, the cosmos is not a fixed, classical entity but a probabilistic wave function. Just as an electron can be in many places at once until measured, the universe itself might have existed in a superposition of possible states at its origin. Quantum cosmology tries to write down the mathematical framework for such a possibility, and in doing so, it offers surprising insights into how something might emerge from apparent nothingness. One of the pioneering ideas in this field comes from the so-called Wheeler-DeWitt equation, named after John Wheeler and Bryce DeWitt. This equation attempts to describe the wave function of the entire universe. Unlike the Schrödinger equation, which describes how a particle evolves in time, the Wheeler-DeWitt equation has no explicit time variable. Instead, time is thought to emerge from the dynamics of the universe itself. This is a radical departure from how we normally think about physics. It suggests that before the universe existed, time as we know it did not exist either. What we think of as the flow of time may only make sense inside a quantum-created universe, not outside of it. Quantum cosmology also allows for the idea that universes can spontaneously appear as quantum fluctuations. In the same way that virtual particles emerge briefly from the quantum vacuum, entire universes might arise as self-contained quantum events. Because quantum physics permits borrowing energy from nothing, as long as it is repaid in accordance with the uncertainty principle, some theorists argue that the birth of a universe might be just a larger-scale version of the same phenomenon. In this picture, nothing is unstable, a fertile ground that can generate universes spontaneously. One particularly famous attempt to describe this process comes from Stephen Hawking and James Hartle, who developed the no-boundary proposal. In their framework, The universe doesn't need an initial singularity, a sharp beginning point at which laws break down. Instead, the universe's wave function describes a smooth origin, without boundaries, like the rounded surface of a sphere. Just as you can travel north on Earth until you reach the North Pole, where direction loses meaning, you can trace time backward until the beginning, where the distinction between before and after vanishes. In this sense, the universe could be finite yet without a true beginning, a concept only accessible through quantum cosmology. Another implication of quantum cosmology is the idea of multiple possible universes arising from the same quantum rules. Just as a quantum particle can take many paths at once, the universe may exist as a vast superposition of possible realities. Some interpretations of this idea align with the multiverse concept, suggesting that different universes, with different laws of physics, all exist in a kind of quantum landscape. We happen to inhabit one branch of this cosmic wave function, the one compatible with our existence. But quantum cosmology also faces formidable challenges. For one, it is extraordinarily difficult to test. Quantum effects dominate at extremely small scales, and the earliest moments of the universe are hidden behind a veil of cosmic expansion. Observational evidence is hard to come by, and mathematical formulations are often incomplete or speculative. The unification of quantum mechanics and general relativity, sometimes referred to as the search for a theory of quantum gravity, remains one of the holy grails of physics. Until we achieve it, quantum cosmology will remain an ambitious but unfinished project. Despite these challenges, the philosophical implications of quantum cosmology are profound. It suggests that the origin of the universe may not require an external cause or a pre-existing condition. Instead, the universe may be the inevitable result of quantum laws themselves. If quantum mechanics permits fluctuations from nothing, then the existence of something may not be surprising at all, it may be required. The question shifts from why is there something rather than nothing, to given the rules of quantum physics, how could nothing ever remain stable? This perspective reshapes our sense of reality. It dissolves the line between nothing and something, showing us that what we call nothingness may itself be structured, active, and creative. It also reframes our place in the cosmos, suggesting that existence itself is a quantum probability, and we are living inside one particular realization of the universal wave function. Quantum cosmology does not offer final answers, at least not yet, but it offers a striking framework for how matter, energy, space, and time could have emerged from nothingness. It embodies the daring spirit of physics, the willingness to push mathematical laws to their limits, to imagine realities that stretch beyond human intuition, and to confront the ultimate questions of existence head-on. The no-boundary proposal is one of the most audacious and mind-bending ideas ever put forward in the quest to understand how the universe began, or more precisely, how it could exist without a traditional beginning at all. Developed by Stephen Hawking and James Hartle in the early 1980s, this idea was an attempt to use the mathematics of quantum mechanics to describe the universe itself. Instead of treating the cosmos as something that needed to be kick-started by an external cause, they asked whether the laws of physics alone could provide a complete account of its origin. The result was a picture so strange and counterintuitive that it challenges the very way we think about beginnings, time, and causality. To unpack the no-boundary proposal, we first need to confront the limitations of classical cosmology. According to Einstein's theory of general relativity, if we trace the expansion of the universe backward in time, we eventually arrive at a singularity, a point of infinite density and curvature, where the laws of physics break down. At this singularity, time as we know it stops, and our equations lose their meaning. For decades, this singularity was seen as the beginning of the universe, but it was also a glaring problem. What does it mean for time to start at a singular point? What caused it? And if physics cannot describe the singularity, how can we say anything about the true origin of the universe? This is where Hawking and Hartle's quantum insight comes in. They proposed that we shouldn't think of time in the early universe in the same way we think of it now. Near the beginning, under extreme conditions, the distinction between time and space might blur. To describe this, they used a mathematical trick known as imaginary time, where time behaves more like a spatial dimension. In ordinary spacetime, we have 3 spatial directions and 1 temporal direction, which flows differently from the others. But in imaginary time, all 4 directions behave like space. What this means for the universe is extraordinary. Instead of having a sharp boundary at a singularity, the universe's geometry could be smooth and finite, like the surface of a sphere. Think about the Earth. Its surface is finite in area, but it has no edge. If you walk north, you eventually reach the North Pole, but there's no boundary where the Earth stops. The no-boundary proposal imagines the early universe in a similar way. If you trace time back far enough, you don't hit a singular edge. Instead, time transforms into something spatial, and the universe smoothly rounds off. In this picture, the universe is finite in extent but has no true beginning. This is why it's called the no-boundary proposal. Just as Earth doesn't need something beyond its surface to define it, the universe doesn't require a before to define its origin. Asking what happened before the beginning of time, in this framework, is like asking what's north of the North Pole. It's a meaningless question, because the concept doesn't apply. The philosophical implications are profound. If the universe has no boundary in time, then it doesn't need an external cause to get started. It is entirely self-contained, governed by its own laws, complete in itself. In Hawking's words, the universe would simply be. It would not need a creator. This doesn't necessarily disprove the existence of a creator, but it shows that from a scientific standpoint, the laws of physics may be sufficient to explain existence without requiring anything outside of them. Of course, the no-boundary proposal is not universally accepted. Some physicists question whether the use of imaginary time is more of a mathematical convenience than a physical reality. Others argue that the proposal is elegant but not testable, making it difficult to judge its validity in the strict sense of science. Yet even if it remains speculative, it represents one of the most creative attempts to deal with the mystery of how the universe emerged without invoking something beyond physics. What makes this proposal so fascinating is that it challenges our most basic intuitions. We are wired to think in terms of beginnings and endings, causes and effects. Everything in our daily lives has a start. A day begins with sunrise, a life begins at birth, a story begins with its first page. To imagine something without a beginning feels almost impossible. But Hawking and Hartle's mathematics suggest that the universe itself might be just such a thing, finite, describable, and yet without a starting point. If true, the no-boundary proposal tells us that time itself is not fundamental but emergent. It arose as the universe expanded and cooled, as quantum fluctuations gave way to classical structures. Before that, there was no before, not because there was a void waiting to be filled, but because the question of before simply has no meaning. The beginning of time is not a sharp edge but a smooth transformation. This reshapes the central question we've been following. How can matter come from nothing? In the no-boundary view, there is no need for matter to spring out of an absolute void. Instead, the universe is a self-contained quantum object, its laws allowing it to exist without a cause, its geometry smoothing out the singularity that would otherwise demand an external explanation. Nothingness, in this case, is not an abyss but a state where the distinction between space and time ceases to exist, giving rise to the structured cosmos we now inhabit. For those who find this unsettling, it's worth remembering that our discomfort comes from trying to impose everyday categories onto the universe itself. Just as quantum mechanics forces us to abandon classical intuitions about particles and waves, quantum cosmology forces us to abandon classical intuitions about beginnings and nothingness. The no-boundary proposal doesn't give us all the answers, but it opens a new way of thinking about existence itself, that perhaps the universe doesn't need a first cause, a starting point, or a boundary. It is simply there, finite yet unbounded, something born not out of nothing but out of the very laws that describe it. Entropy is one of those concepts that seems simple on the surface but reveals astonishing depth when you apply it to the cosmos. In everyday life, entropy is often described as disorder: ice melting into water, a tidy room turning messy, a drop of ink spreading through clear liquid. The second law of thermodynamics tells us that entropy tends to increase over time. Left to itself, a system moves towards states of higher disorder, higher entropy. Yet when we look at the universe, we see a story that seems paradoxical. It started in a state of incredibly low entropy, and from that foundation arose the galaxies, stars, planets, and life forms we know today. This invites one of the deepest questions in cosmology. How did the universe evolve from something so seemingly featureless into the richly structured reality we inhabit? To understand this, we need to look at the concept of entropy more closely. Entropy is not just about messiness or disorder in the everyday sense. It is a measure of the number of possible microscopic configurations that correspond to a given macroscopic state. A deck of cards shuffled randomly has high entropy because there are countless arrangements consistent with shuffled. A deck in perfect order has low entropy because only a tiny fraction of arrangements qualify. When applied to the entire universe, entropy tells us about the possible states of matter, energy, and space-time itself. Now here's the puzzle. The Big Bang, far from being a chaotic explosion, appears to have been a state of remarkably low entropy. The universe was hot, dense, and nearly uniform. Why is this surprising? Because a uniform distribution of matter might look disorderly to us, but gravitational physics flips our intuition. Gravity has a peculiar relationship with entropy. In most systems, spreading things out increases entropy. Gas molecules dispersing in a room, for example. But under gravity, clumping actually increases entropy. A cloud of gas collapsing into a star is a move toward higher entropy because there are vastly more microscopic arrangements corresponding to a collapsed state than to a perfectly smooth one. By this logic, the early universe, smooth, homogeneous, nearly featureless, was in an incredibly low entropy state, teetering on the edge of possibilities. As the universe expanded, gravity took over, allowing matter to clump and structures to form. Tiny fluctuations in density, quantum in origin, were amplified by cosmic inflation and became the seeds of galaxies. Those clumps represented an increase in entropy. Stars ignited, galaxies swirled, planets formed. Each stage was a progression toward higher entropy, not away from it. What looked like order emerging from chaos was actually entropy playing out on cosmic scales. The order we perceive, the magnificent spirals of galaxies, the delicate balance of planetary orbits, is not a violation of the second law but a consequence of it, mediated through gravity's unusual relationship to entropy. This realization reshapes the way we think about nothing. When we say the universe began in a state of low entropy, we might be tempted to equate that with emptiness or nothingness. But it was not an absolute void. It was a finely tuned, extraordinarily simple starting point with very few allowable configurations. Some physicists argue that this state is what allowed the universe to give rise to complexity. If the universe had started already in maximum entropy, like a featureless soup of energy spread uniformly, there would have been no room for evolution, no potential for stars or life. The arrow of time, the flow from past to future, exists only because the universe began in a state far from equilibrium. Why the universe began in such a low entropy condition is one of the great mysteries of modern science. Roger Penrose has famously argued that the initial entropy was unimaginably special, so finely tuned that it seems almost miraculous. Others suggest that the inflationary epoch may explain it, smoothing out irregularities and resetting the entropy clock. Still others turn to speculative ideas like the multiverse, where our universe's low entropy beginning is simply one possibility among many. What's remarkable is that this low entropy beginning made everything possible. Without it, there would be no galaxies, no stars, no chemistry, no biology. Entropy is often thought of as the destroyer, the law that guarantees the eventual heat death of the universe, when everything will spread into featureless equilibrium. But in the early cosmos, entropy's increase was the engine of creation, driving the emergence of complexity from simplicity. It is not merely the enemy of order. It is the story of how order arises, temporarily, against a backdrop of inevitable decay. So how do we connect this to the question of matter from nothing? The low entropy beginning can be seen as a kind of cosmic nothingness, not absolute void, but a state of extreme simplicity, a blank canvas of sorts. From that canvas, the dynamics of physics allowed structure to bloom. The laws of thermodynamics, coupled with quantum fluctuations and gravity, turn simplicity into richness. The fact that we live in a structured universe at all is evidence of the strange and delicate conditions at its birth. Entropy, then, is the bridge between nothing and something, between simplicity and complexity. It explains how galaxies could emerge from near uniformity, how life could arise from chemistry, and why time flows in one direction. It also leaves us with a profound puzzle. Why did the universe start in such a low entropy state in the first place? That question, like so many in cosmology, pushes us beyond current science into realms of speculation and philosophy. Perhaps one day we will find an answer. For now, we can say this much: the arrow of time, the growth of structure, and the very possibility of existence all trace back to that improbable, low-entropy beginning that looked like nothing, and yet contained the seeds of everything. The idea that mathematics might be the ultimate foundation of reality is one of the most profound and unsettling possibilities in human thought. It suggests that the universe itself, its matter, its forces, its space and time, could arise not from a physical cause but from the very logic of mathematics. In this view, nothing is not a void but a landscape of mathematical truths, eternal and independent of physical existence. And perhaps those truths are powerful enough to call a universe into being. At first glance, this may sound abstract, even mystical, but the more we examine it, the more compelling it becomes. Mathematics has always had an uncanny ability to describe the natural world. Equations written on paper turn out to govern the behavior of planets, the motion of particles, the bending of light, and the evolution of galaxies. The predictive power of mathematics is so extraordinary that Nobel laureate Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. Why should the universe obey mathematical laws at all? Why should numbers, patterns, and abstract symbols conceived in human minds correspond so precisely to physical reality? One radical answer is that mathematics doesn't just describe the universe, it is the universe. This is the idea championed by thinkers like Max Tegmark, who proposed the mathematical universe hypothesis. According to this view, mathematical structures are not just useful tools, they are ontologically real. A triangle, a group, a set of equations, these things exist independently of our minds. And if they exist, then perhaps the physical world is simply one such mathematical structure. Our universe is not governed by math, it is math, taking physical form. How does this connect to the question of something from nothing? If mathematics exists necessarily, outside of time and space, then it provides a framework where universes can emerge spontaneously. Just as 2 plus 2 is equal to 4 is a truth that exists whether or not anyone writes it down, the equations that describe a universe could exist whether or not anyone observes them. In this sense, reality might spring into existence because mathematics allows it, because the equations describing spacetime and quantum fields inherently contain the possibility of realization. Consider, for example, the balance of energies in the universe. As we discussed earlier, matter and gravitational energy may cancel out, yielding a net energy of zero. That possibility is not just physical, it is mathematical. Zero is a mathematical truth. The symmetry that allows matter and antimatter to exist in pairs is also a mathematical feature. The wave functions that describe quantum states are mathematical objects. If the laws of mathematics exist independently, then universes might not need an external trigger. They may simply exist because the mathematical possibility of their existence cannot be denied. Some philosophers have gone even further, arguing that mathematics is more real than physical matter. Physical things decay, crumble, and transform. But the number 3 never ceases to exist, nor does the Pythagorean theorem. These truths are eternal. If that's the case, then the emergence of physical reality may not require a cause beyond the fact that mathematical structures are inevitable. Our universe might be one instantiation of an infinite set of possible mathematical realities. Of course, this idea raises as many questions as it answers. For one, what does it mean for mathematics to exist? Is it a Platonic realm, beyond time and space, where numbers and equations live independently? Or is mathematics a language our minds impose upon reality? If the latter, then mathematics may be descriptive rather than generative. But if the former, then mathematics may be the deepest foundation of existence, the source from which something inevitably arises. Skeptics argue that this is more philosophy than physics, since it's difficult to test. But some scientists point out that if the universe is a mathematical structure, then its consistency and simplicity are exactly what we would expect. The fact that nature can be described with elegant equations, like Einstein's E=mc² or Schrödinger's wave equation, is evidence that mathematics is not just a convenient tool but the very language of reality. The more we probe, the more mathematical the universe seems to be. There is also a provocative twist. If all mathematical structures exist, then perhaps all possible universes exist too. Every consistent mathematical system could correspond to a real universe, even if its laws are entirely unlike ours. This idea connects back to the multiverse hypothesis, but with a sharper edge. It suggests a multiverse not just of physical possibility, but of mathematical inevitability. Our universe is simply the one whose mathematical structure happens to allow conscious observers. In this sense, nothing may never truly be nothing. Even in the absence of space, time, matter, and energy, mathematics remains. And if mathematics remains, then reality is unavoidable. As long as mathematical truths exist, existence itself cannot be denied. The laws of logic and numbers may be the primordial canvas on which the universe was painted. This perspective doesn't settle the debate. It opens new ones. Is mathematics discovered or invented? If discovered, then it exists independently, and perhaps the universe is a manifestation of its timeless truths. If invented, then why does it describe the universe so perfectly? Either way, mathematics seems too deeply woven into reality to be dismissed as mere coincidence. So when we ask how matter could come from nothing, the mathematical view offers one answer. It arises because nothing is never truly void. Beneath the emptiness lies the inevitability of mathematics, and from that inevitability, universes like ours may spontaneously unfold. Existence, in this view, is not a miracle or a fluke but the most natural consequence of mathematical truth itself. Time is so deeply embedded in our experience that it feels impossible to imagine reality without it. Our lives are measured in moments, days, years. The cosmos itself is narrated as a story with a beginning, middle, and possible end. Yet, when we probe the origins of the universe, a startling possibility emerges. Time itself may not have always existed. Instead, it may have been born alongside matter, space, and energy, emerging from the very conditions that gave rise to the cosmos. In that case, asking what happened before the universe may not make sense at all, because there was no before to speak of. To grasp this idea, let's begin with Einstein's theory of general relativity. In Einstein's framework, time is not an independent background that ticks away universally. It is woven together with space into a four-dimensional fabric called spacetime. Gravity, in this view, is not a force pulling objects but the curvature of this fabric caused by mass and energy. This revolutionary insight already changed our understanding of time, showing us that it is not absolute. Time runs differently depending on gravity and motion. A clock on Earth ticks differently than a clock on a satellite in orbit, and both differ from a clock near a black hole. Time is flexible, relative, and inseparable from the physical universe itself. When we trace the universe back to its earliest moments, the Big Bang, we are not simply watching matter and energy condense. We are watching space-time itself contract. At that singular point, all the dimensions we know, including time, collapse to a boundary where the laws of physics as we understand them cease to apply. This raises the question, was time itself created in that instant? Many physicists say yes. Time, like space, came into being at the Big Bang. Asking what happened before is like asking what's north of the North Pole. It's a question that assumes a framework that doesn't exist. Quantum cosmology strengthens this perspective. When physicists like James Hartle and Stephen Hawking developed the no-boundary proposal, they suggested that in the earliest phases of the universe, time behaved more like space. The boundary we think of as the beginning wasn't a sharp edge but a smooth transition, where the distinction between time and space was blurred. In this view, time as we experience it, flowing forward, with a past, present, and future, emerged gradually as the universe cooled and expanded. Time is not primordial, it is emergent. This idea echoes in many areas of theoretical physics. Some researchers argue that time might arise from quantum entanglement, the mysterious connection between particles. According to this line of thought, the ordering of events we experience as time could be a large-scale effect of correlations between quantum states. Others suggest that time could be an emergent property of thermodynamics. The increase of entropy provides the arrow of time, and without entropy gradients, time as we know it would have no direction. In both cases, time is not a fundamental ingredient of the universe but a phenomenon that arises from deeper laws. Philosophically, this is one of the most challenging ideas for us to accept. Our minds are tuned to think causally, this happened, then that. We instinctively ask what came before and what comes after. But if time itself is not fundamental, then such questions may not apply to the origin of the universe. The universe doesn't need a before in which to be created, because before is a concept that only makes sense after time has emerged. This challenges our ordinary language, which is built on temporal assumptions. To say the universe began may be misleading, because beginning implies a timeline that stretches behind it. A more accurate phrasing might be that the universe exists as a whole, with time as one of its internal dimensions. The emergence of time also reshapes our understanding of nothingness. If we imagine nothing as a timeless void, then the birth of the universe is the birth of time itself. But if time does not exist in nothingness, then nothingness cannot be described as timeless either. It simply cannot be described at all. Our concepts of before, after, duration, and sequence break down in the absence of time. This means that nothing may not be a background waiting for something to happen in it, but rather a state where the very idea of happening has no meaning. What makes this so radical is that it forces us to reconsider our most basic assumptions about reality. If time is emergent, then the laws of physics may not play out on a pre-existing stage. Instead, the stage itself is part of the play, created and sustained by the same physical processes that govern matter and energy. And if that's true, then the origin of the universe is not about matter appearing in empty time, but about time, space, and matter all arising together from a deeper, perhaps timeless, foundation. In practice, this shifts the ultimate question. We often ask, what caused the universe to exist at this moment rather than some other? But if time began with the universe, the question of why then dissolves. There was no then. The universe's existence is not an event in time but the origin of time itself. From that origin, the flow of seconds, minutes, and eons became possible, eventually leading to stars, galaxies, and life. So the emergence of time is central to understanding how something could arise from nothing. It shows us that nothing may not precede something in any temporal sense, because the very act of emergence included the birth of time itself. We live inside that emergence, moving forward along the arrow of entropy, measuring moments, remembering the past, anticipating the future. All because the universe, at its birth, unfolded not just matter and energy, but the very dimension that makes sequence possible. The observer effect in quantum mechanics is one of the most bewildering and philosophically charged aspects of modern science. At its heart, it suggests that the mere act of observation, of measurement, can influence the outcome of physical processes. This notion seems to blur the line between the objective world and the subjective role of consciousness, hinting that reality as we know it may not be fully independent of the act of being observed. When we link this idea to the question of how matter could arise from nothing, it invites the possibility that observation itself could play a fundamental role in shaping existence. To grasp this, we need to recall what quantum mechanics teaches us about the behavior of particles at the smallest scales. Unlike the familiar world of classical physics, where objects have definite positions, velocities, and trajectories, the quantum realm is governed by probabilities. A particle like an electron doesn't travel along a single path, it exists as a cloud of potential locations, described by its wave function. That wave function doesn't tell us where the particle is, but only the probabilities of where it might be if measured. This brings us to the famous double-slit experiment, perhaps the most striking demonstration of the observer effect. When electrons are fired at a barrier with two slits and no one observes which slit they pass through, they behave like waves, creating an interference pattern on a screen behind the barrier. Each electron seems to go through both slits at once, interfering with itself. But when scientists set up a detector to observe which slit an electron goes through, the pattern changes. The electron no longer behaves like a wave but like a particle, passing through one slit or the other. The act of measurement collapses the wave of probabilities into a definite outcome. This experiment is not limited to electrons. It has been repeated with photons, atoms, and even molecules composed of thousands of atoms. The result is always the same. When unobserved, quantum systems behave like waves of probability. When observed, they snap into a single reality. This raises an astonishing question. Does observation create reality? Physicists are divided on how to interpret this. One interpretation, known as the Copenhagen interpretation, suggests that reality at the quantum level is inherently indeterminate until it is measured. In this view, the act of observation collapses the wave function into a concrete state. Another interpretation, called the many worlds hypothesis, argues that the wave function never collapses at all. Instead, every possible outcome happens, but in different branches of a vast multiverse. From this perspective, observation doesn't create reality. It simply determines which branch of the multiverse we experience. But the most philosophically provocative interpretation is the idea that consciousness itself plays a role. If observation requires a conscious observer, then our awareness is somehow entangled with the unfolding of physical reality. Thinkers like John von Neumann and Eugene Weiner once entertained this possibility, suggesting that the mind might be the final step in collapsing the wave function. While most physicists today are cautious about linking consciousness to quantum mechanics, the fact remains that we don't yet fully understand what observation really means at the quantum level. Is it any interaction with the environment, such as a particle hitting a detector? Or does it require something deeper, like awareness? When we tie this back to the origin of matter, the implications are staggering. Could it be that the universe itself requires some kind of observation to crystallize into existence? If so, who or what was the observer at the dawn of time? Some propose that the universe may be self-observing, quantum fields interacting with themselves, collapsing probabilities into realities through constant entanglement and interaction. Others speculate that consciousness might be more fundamental than we realize, not an emergent property of matter but a feature of reality itself, interwoven with the fabric of the cosmos. Even if we avoid the leap into consciousness, the observer effect challenges the notion of an entirely independent reality. It suggests that potential and actuality are not the same, and that the bridge between them may depend on processes that resemble observation. This introduces a curious possibility. In a state of nothing, where only probabilities exist, observation, whether through interaction, entanglement, or awareness, could serve as the mechanism that brings something into being. In this sense, nothing might be a sea of unrealized potential, and observation the spark that ignites reality. There are also deeper philosophical echoes here. If reality is influenced by observation, then perhaps existence itself is participatory. John Wheeler, a pioneer of quantum theory, famously proposed the participatory universe idea. He suggested that the universe requires observers to fully exist, and that by observing the cosmos, we help bring it into being. This is not to say we created the universe, but that the act of observation is fundamental to its ongoing reality. Wheeler summarized this with the phrase, "No phenomenon is a real phenomenon until it is an observed phenomenon." For a YouTube audience wrestling with the idea of matter from nothing, this is a thrilling and unsettling thought. The observer effect implies that the universe is not a passive stage on which events unfold, but a dynamic interplay between possibility and realization, probability and actuality. If observation is part of that interplay, then the line between subject and object, between mind and matter, may not be as sharp as we assume. Ultimately, the observer effect leaves us with more questions than answers. Does observation truly shape reality, or does it merely reveal what was already determined? Is consciousness necessary, or is interaction enough? And could the act of observation itself be the key to turning nothing into something? Science has not yet resolved these mysteries, but they remain at the frontier of both physics and philosophy, a reminder that reality may be far stranger than our everyday experience suggests. When we talk about the vacuum in physics, we often imagine it as the closest thing to nothing, a state stripped of all matter, devoid of particles, as empty as emptiness can be. But as we've seen, quantum mechanics complicates this picture. The vacuum is not truly empty. It buzzes with fluctuations, with virtual particles flickering in and out of existence. And here lies an even deeper possibility. What we call the vacuum, the baseline of physical reality, might not be the ultimate ground state. It might be a temporary, unstable condition, something that could, under the right circumstances, decay into a different, perhaps lower energy vacuum. This idea is known as vacuum instability, and it has unsettling implications for the nature of reality, for the origin of the universe, and even for its ultimate fate. To understand this, let's step back to the concept of energy levels. In quantum field theory, every field, the Higgs field, the electromagnetic field, and so on, has a configuration that corresponds to a certain energy. The vacuum state is the lowest energy configuration available to that field. But what if the vacuum we currently occupy is not truly the lowest possible energy? What if it's a false vacuum, a kind of local minimum, stable for now, but not the absolute bottom of the energy landscape. Imagine a ball resting in a small valley on the side of a mountain. From the ball's perspective, it feels stable. It's not rolling anywhere, and as long as no disturbance comes along, it could stay there indefinitely. But higher up the mountain lies the rim of the valley. Beyond that rim is a deeper valley, the true minimum of the landscape. If the ball were nudged just enough to cross the rim, it would roll down into the deeper valley and settle there permanently. The false vacuum is that small valley, and the true vacuum is the deeper one. If our universe exists in a false vacuum, then reality as we know it is precarious. The fields that define the properties of matter, the Higgs field, for example, could one day shift into a more stable configuration. That shift would release enormous amounts of energy, rewriting the fundamental rules of physics in the process. Particles would acquire different masses, forces could change in strength or disappear, and atoms as we know them could no longer exist. Entire structures, stars, planets, life, would be obliterated in an instant. This catastrophic event is called vacuum decay, and it would expand outward at the speed of light, reshaping the universe as it goes. The terrifying part is that if such a transition were to happen, we would never see it coming. The bubble of true vacuum would sweep across space faster than any signal could warn us. One moment, the laws of physics would be as we know them. The next, everything would be unrecognizably different. From our perspective, the universe would simply vanish. Now, before panic sets in, it's important to stress that this is a theoretical possibility, not a prediction that it will happen anytime soon. The stability of our vacuum depends on the values of fundamental constants, like the mass of the Higgs boson and the top quark. With current measurements, many physicists believe we may be on the edge of what's called metastability, a state where the vacuum is stable enough to last for billions or even trillions of years, but not necessarily eternal. If that's the case, the universe is safe for now, but not guaranteed forever. But here's where the connection to our theme becomes fascinating. If our vacuum is not the true vacuum, then what we call nothing is not ultimate. Beneath it lies a deeper, more fundamental state. And if the vacuum can change, then the very laws of physics can change with it. This reshapes our concept of nothingness. The vacuum is not the absence of reality. It is itself a dynamic, physical entity with properties that can evolve. Our universe may not be resting on an immutable foundation, but on a precarious plateau in a shifting landscape of possibilities. Some cosmologists even suggest that our universe may have been born from such a transition. In this picture, what we call the Big Bang could have been the result of a vacuum decay in a higher energy field. A false vacuum, unstable and bubbling, could have released its energy in an inflationary expansion, creating space, time, and matter as it decayed into a lower energy state. In this way, vacuum instability is not just a threat to the future, it might also be the key to the past, the mechanism by which something first emerged. This ties back to the question of matter from nothing. If the vacuum itself can be unstable, then nothing is revealed as a creative force. It is not an inert backdrop but a seething potential, capable of transforming into different realities. Each vacuum state corresponds to a different set of physical laws. What we call something, matter, energy, forces, could simply be the expression of our current vacuum's properties. And nothing in a deeper sense might be the transition between vacua, the quantum instability that allows universes to bloom. Philosophically, vacuum instability blurs the line between permanence and impermanence. It suggests that even the foundations of physics are not eternal. The laws we take as absolute may themselves be emergent, contingent on the stability of the vacuum we inhabit. What we call reality might be only one chapter in a longer story of shifting vacua, with other possible universes existing in other valleys of the energy landscape. For a YouTube audience, this is both terrifying and awe-inspiring. On one hand, it's humbling to realize that the universe we know rests on fragile ground, potentially doomed to collapse into something alien and unrecognizable. On the other hand, it's exhilarating to think that such instability may be the engine of creation itself, that universes can arise, evolve, and vanish as the vacuum shifts from one state to another. Nothingness, in this sense, is not absence but possibility. So vacuum instability teaches us that nothing is never final. What looks like the ultimate ground may only be a temporary resting place, pregnant with the potential to transform. Our existence depends on the stability of a vacuum state that may not last forever, but it is precisely such instability that may have given birth to our universe in the first place. In the grand scheme, perhaps nothing is not emptiness at all, but a cosmic tension between what is and what could be. As we've journeyed through the ideas of cosmology, quantum theory, relativity, and philosophy, one truth becomes increasingly clear. Science is remarkably powerful at modeling how the universe works, but it may never fully answer why the universe exists in the first place. This distinction between how and why is crucial, because it marks the boundary between the domain of science and the deeper, perhaps unanswerable, questions of philosophy and metaphysics. Science is a tool for building models. It asks, given a set of assumptions and laws, what follows? How do galaxies form under the pull of gravity? How do particles interact in quantum fields? How does energy flow and transform in stars? These are questions about mechanisms, processes, and predictions. And science excels at them. The beauty of the scientific method is that it provides a consistent framework to test these models against reality, refining them until they match the patterns we observe. But when we turn the question around, when we ask not just how the universe behaves but why it exists at all, we quickly enter murkier territory. For instance, cosmologists can describe in extraordinary detail how the universe evolved from a hot, dense plasma into the vast structure of galaxies we see today. They can even speculate on how quantum fluctuations might have triggered the birth of space and time. Yet these models all start with certain assumptions: the existence of quantum fields, the validity of mathematics, the reality of physical laws. Science can show how these ingredients interact, but it cannot explain why those ingredients exist at all, or why there is a universe in which they can exist. Consider the law of conservation of energy. Physics can show us how energy is balanced, transferred, and conserved across every process we know. But it cannot explain why such a law exists in the first place. Why should the universe obey rules at all? Why not chaos, with no consistency, no lawfulness, no patterns? Or consider the fundamental constants, the speed of light, the strength of gravity, the mass of the electron. Science can measure these constants and use them to make predictions, but it cannot answer why they have the values they do, or why they exist instead of some other set. If they were even slightly different, our universe might not permit stars, planets, or life. Why these numbers and not others? This is where philosophy inevitably enters. The why questions often step beyond the limits of testable hypotheses. Philosophers and theologians have long debated whether the universe exists because of necessity, it had to exist, contingency, it could have existed otherwise but happens to exist, or pure chance, it exists for no reason at all. Science can engage with these ideas, but it cannot settle them. The tools of observation and experimentation are not equipped to probe ultimate purpose. Stephen Hawking, who spent much of his career pushing science toward the edges of these mysteries, once remarked that even if we had a theory of everything that explained all the physical laws, we would still be left with the question: why does the universe bother to exist at all? Why is there something instead of nothing? That final question seems to transcend the explanatory power of equations. And yet, there is a profound beauty in acknowledging this limit. Far from being a weakness of science, it is a reminder of humility. Science gives us astonishing clarity about the workings of the universe, but it doesn't pretend to have every answer. The deepest origins may always remain partly philosophical, resting on assumptions that cannot themselves be derived. Even the most elegant models, like the no-boundary proposal or the multiverse hypothesis, ultimately push us to confront mysteries that may never be reduced to simple explanations. For some, this is frustrating. We crave closure, a final answer that explains everything. But perhaps the openness is what gives the question its power. The mystery of why existence exists invites wonder, reflection, and creativity. It forces us to step beyond the realm of certainty and dwell in the realm of possibility. It keeps alive the ancient human drive to ask, to question, to seek meaning. Science, then, is not diminished by its inability to answer why. It is defined by it. Its domain is the how, the precise, testable unfolding of processes. The why may forever belong to philosophy, to metaphysics, and perhaps to personal belief systems. When we conflate the two, we risk misunderstanding what science is for. But when we respect the boundary, we see how each domain complements the other. Science illuminates the mechanisms of reality, while philosophy and metaphysics wrestle with its ultimate significance. In the end, the limit of explanation is not a barrier but an invitation. It reminds us that the universe is richer than any single framework can capture. Physics can describe the dance of galaxies and the quantum foam, but the question of why there is a dance at all is left hanging, waiting for each of us to wrestle with in our own way. Perhaps the most honest stance is to live in awe of the mystery, embracing the balance between knowledge and wonder. When science reaches the edges of what it can explain, philosophy steps in to explore the broader landscape of possibility. The question of how matter, existence, and reality itself could arise from nothing has been a central theme of metaphysical thought for millennia. Across cultures and traditions, thinkers have proposed different frameworks to account for why there is something rather than nothing. Though these ideas differ in detail, they often cluster around three broad perspectives: creation, necessity, and pure chance. Each offers a unique lens for interpreting existence, and each raises as many questions as it answers. The first perspective, creation, is perhaps the oldest and most intuitive. It posits that the universe exists because it was brought into being by some external agency, a metaphysical principle beyond the universe itself. This idea resonates because it provides a satisfying causal structure. If everything within the universe has a cause, then the universe as a whole must have a cause as well. But of course, this raises its own profound question: what caused the Creator? If the explanation for the universe is a timeless, necessary being, then why does that being exist rather than nothing at all? For some, this is where faith enters, a willingness to accept a fundamental cause beyond further explanation. For others, it feels like shifting the problem one step back without solving it. The second perspective, necessity, takes a different route. It suggests that the universe exists because it must. Reality, in this view, is not optional. It is baked into the logic of existence itself. Philosophers such as Spinoza argued that the universe is necessary because it is an expression of infinite substance. It cannot not exist. More recently, some physicists and philosophers have speculated that the laws of mathematics or logic may themselves require that something exists. For instance, if nothingness is unstable, then something is inevitable. In this framework, the question "why is there something rather than nothing?" may be misguided, because the answer is simply, there is no alternative. This idea of necessity can take many forms. It might be metaphysical, as in Spinoza's vision of infinite substance. It might be logical, as in the argument that nothing is impossible because it cannot be defined without reference to something. Or it might be physical, as in the claim that quantum fields and fluctuations are unavoidable features of reality. But in each case, necessity denies the possibility of true nothingness. Something exists because it must exist, and the universe is the unavoidable manifestation of that necessity. The third perspective, pure chance, embraces the possibility that there is no deeper reason at all. In this view, the universe exists not because it was created, nor because it had to, but simply because it does. Existence is brute fact. There is no explanation beyond that. For some, this is unsatisfying, even unsettling. It offends our desire for order, our instinct to find causes, patterns, and reasons. Yet for others, it is liberating. To accept the universe as a brute fact is to acknowledge the limits of explanation and to free ourselves from the endless regress of causes. This perspective has echoes in modern physics as well. The multiverse hypothesis, for example, suggests that countless universes exist, each with different properties. In such a framework, our universe may simply be one of many, with no special reason for its existence other than chance. The fact that we are here to observe it is not because it was created for us, nor because it was inevitable, but because only in universes with the right conditions for life could observers like us exist. This is the anthropic principle. We see this universe not because it was designed, but because we couldn't exist in any other kind. Each of these three perspectives, creation, necessity, and chance, provides a different kind of answer, but none closes the case. Creation gives us a cause but leaves the cause itself unexplained. Necessity removes the need for a cause but risks being too abstract to satisfy. Chance dispenses with explanation altogether but leaves us with a universe that feels arbitrary. The enduring puzzle of why there is something rather than nothing may persist because none of these frameworks is fully graspable to the human mind. Still, engaging with these ideas is valuable, not because they settle the question but because they sharpen our sense of the mystery. Creation reminds us that existence could be rooted in purpose. Necessity reminds us that existence might be unavoidable. Chance reminds us that existence may be a matter of luck, with no deeper reason. Each stretches our imagination, challenging us to confront the possibility that the ultimate answers may lie forever beyond our comprehension. At the same time, these perspectives intersect with science in surprising ways. The notion of necessity resonates with the idea of mathematical structures or physical laws being inevitable. The idea of chance aligns with quantum uncertainty and multiverse theories. And creation resonates with the philosophical question of whether the universe could be self-caused, as Hawking once suggested. The interplay of metaphysics and science keeps the question alive, refusing to let it fade into complacency. In the end, the philosophical takes on creation, necessity, and chance remind us that the deepest questions about reality are not only scientific puzzles but human ones. They call us to reflect on meaning, purpose, and the boundaries of reason itself. Whether we lean toward logical necessity or brute fact, we are forced to confront the ultimate mystery with humility. The question of why there is something instead of nothing may never yield a definitive answer, but it continues to shape how we think about ourselves, our universe, and our place within it. For all the progress humanity has made in science, sending spacecraft beyond our solar system, probing the quantum world, and mapping the faint afterglow of the Big Bang, we must acknowledge a sobering truth: the deepest origins of the universe remain unknown. We stand with powerful tools in hand, yet still in the shadow of profound mystery. And this is where scientific humility becomes essential. Humility in science doesn't mean resignation or defeat. It means recognizing the limits of what we currently know while remaining open to discovery. It means embracing uncertainty not as failure, but as opportunity. When scientists admit that they don't yet have the answers, they are not conceding weakness, they are demonstrating the strength of intellectual honesty. The origin of matter, the emergence of space-time, the reason why there is something rather than nothing, these are questions so vast that any claim of certainty would be premature. Instead, humility keeps the scientific enterprise honest and alive. Take the Big Bang Theory as an example. It is one of the most successful models in cosmology, supported by overwhelming evidence. The cosmic microwave background radiation, the abundance of light elements, and the expansion of galaxies. But even with its success, the Big Bang is not a complete theory of origins. It describes how the universe evolved from a hot, dense state, but it does not explain what caused that state, what preceded it, if such a concept is even meaningful, or why the laws of physics themselves existed to govern it. The Big Bang gives us the how, but not the ultimate why. Or consider quantum mechanics. Its predictions are among the most accurate in all of science, matching experimental results to astonishing precision. Yet its interpretation remains unsettled. We know how to use quantum mechanics to calculate probabilities, but we don't fully understand what those probabilities mean about reality. Do particles truly exist in multiple states at once until measured? Does every possibility happen in parallel universes? Is consciousness involved? Science has not reached consensus, and perhaps it never will. This lack of closure is not a failure. It's a reflection of the humility needed when grappling with phenomena that defy our everyday intuitions. Even our most ambitious theories, like string theory or loop quantum gravity, which attempt to unify quantum mechanics with general relativity, remain speculative. They are elegant mathematical frameworks that could reveal how space-time itself emerges from deeper structures. But they are not yet proven. We do not know if they are correct, or if the universe follows rules we haven't even imagined. This uncertainty reminds us that the journey of discovery is ongoing. We are, in a sense, still in the early chapters of the story. Scientific humility also means resisting the temptation to overextend. When Stephen Hawking suggested that the universe could be self-contained, requiring no creator, he was offering one possible framework, not a definitive closure. When physicists speculate about multiverse or no-boundary proposals, they are acknowledging possibilities, not certainties. Science thrives not by declaring ultimate truths, but by testing ideas, discarding those that fail, and refining those that survive. The humility lies in knowing that every answer may lead to deeper questions. This humility has a philosophical dimension too. The human mind craves certainty, but the universe may not grant it. Perhaps the question of ultimate origins is structured in such a way that our tools, language, mathematics, observation, cannot fully capture it. Just as a fish cannot comprehend life outside water, we may not be equipped to grasp what nothing truly means or why existence exists at all. Scientific humility accepts this possibility while still striving to push the boundaries as far as they will go. It is also worth noting that humility is not just a stance toward knowledge, it is also a driver of progress. Admitting what we do not know creates the space for new generations of thinkers to ask bolder questions. The realization that Newton's laws were not the final word opened the way to Einstein's relativity. The recognition that relativity and quantum mechanics do not mesh opened the search for quantum gravity. Each step forward begins with the courage to say, "We don't yet know." For a YouTube audience, this is an important message. The pursuit of cosmic origins is not about having all the answers neatly tied up. It is about embracing the grand mystery while celebrating the progress we have made. Scientific humility keeps us grounded in, or rather than arrogance. It tells us that the cosmos is not a puzzle we will solve once and for all, but a mystery that will continually unfold, revealing new layers with every discovery. So when we ask how matter could arise from nothing, we must hold both curiosity and humility together. Curiosity drives us to seek explanations. Humility reminds us that our current answers are partial, provisional, and open to revision. This balance is not weakness, it is the strength of science, the honesty to admit ignorance while daring to explore the unknown. After traveling through the labyrinth of theories, from quantum fluctuations to multiverse speculations, from philosophical nothingness to the shimmering possibility of cosmic necessity, there is a point where all the complexities fade, and we are left with a single breathtaking truth. The fact that we exist at all to ask these questions is itself astonishing. If you strip away the physics, the metaphysics, the mathematical frameworks, and the philosophical debates, what remains is a sense of pure wonder at being here, conscious, curious, alive, in a universe that could just as easily not have been. Think of the improbability of it all. 14 billion years ago, the universe was a hot, dense plasma of particles. Out of that fireball, through a chain of events governed by laws that might themselves be emergent or contingent, galaxies formed, stars ignited, planets coalesced, and one tiny blue world came to orbit an average star in a quiet arm of the Milky Way. On that world, life arose, not once, but in countless branching pathways. And eventually, through eons of trial, error, mutation, and adaptation, life developed the capacity for self-awareness. Eyes opened, minds sparked, and eventually, we began to ask questions, not just about survival, but about the very nature of existence itself. The question, why is there something rather than nothing, is not just a scientific puzzle, it is an expression of our deepest capacity for reflection. Rocks don't ask such questions. Stars don't wonder about their origins. But human beings do. That fact alone, that matter organized itself into structures capable of questioning its own existence, is perhaps as miraculous as anything science can describe. We often take existence for granted because we are immersed in it every moment of our lives. But pause for a moment and consider how strange it is that there is anything at all. Out of all the possible ways reality could have unfolded, here we are, in a universe vast enough to contain billions of galaxies, intricate enough to support life, and mysterious enough to challenge the very limits of comprehension. That sense of wonder transcends scientific explanation. It doesn't matter whether the ultimate answer lies in quantum cosmology, mathematical necessity, or sheer chance. The fact that something exists, and that we exist within it, is already an astonishing gift. And wonder is not just a passive feeling, it is a driving force. It propels science forward, fuels philosophy, inspires art, and shapes spirituality. Every great leap of understanding begins with someone daring to be amazed. To look at the night sky and not just see points of light, but to feel the immensity of space, the depth of time, the mystery of being, that is wonder in its purest form. Without it, there would be no drive to explore, no hunger to know, no journey from ignorance to discovery. Even the most advanced scientific models cannot remove the element of awe. If we learn that the universe emerged from quantum fluctuations, we can still marvel at the fact that the laws of quantum mechanics exist at all. If we embrace the multiverse idea, we can still marvel that we inhabit one universe where conditions allow for life. If we conclude that existence is necessary, we can still marvel at the beauty of necessity itself. Wonder does not end when we find answers, it deepens, because each answer only reveals new mysteries. Perhaps this is the real point. We seek to know whether matter can come from nothing, whether time had a beginning, whether laws emerge from chaos. But even if one day we assemble a perfectly coherent explanation, the question will not lose its power. The very act of asking, the very fact that there are beings in this cosmos who can reflect upon it, is itself a miracle beyond explanation. And maybe that is the heart of the matter. In the end, it is not only about equations or metaphysics. It is about the wonder of being here at all, able to think, to feel, to imagine, and to ask. The universe could have been silent and lifeless, but it isn't. Instead, it has given rise to consciousness that can ponder its own origins. That is the ultimate wonder. When we arrive at the end of this long journey through cosmology, physics, and philosophy, it's tempting to crave a definitive answer. We want closure, a single statement that resolves the riddle of how matter could arise from nothing. But perhaps the greatest insight we can carry with us is that nothing may never have been truly nothing in the first place, and in that realization lies the key to everything. Think back to how slippery the word nothing has proven to be. In philosophy, it meant absolute emptiness. No space, no time, no laws, no potential. But science taught us that even what looks like empty space is not truly empty. The vacuum is alive with quantum fluctuations, with virtual particles appearing and disappearing in a restless dance. Gravity itself may balance the energy ledger, allowing a universe to emerge without violating conservation. The Higgs field permeates the cosmos, giving mass to particles. The vacuum may even be unstable, hinting at deeper layers beneath what we call reality. Each time we probe nothing, we find something hiding there, something subtle, something profound. And maybe this is the secret. Maybe nothing is not an absence but a fertile ground of possibility. What we once imagined as emptiness may in fact be the most fundamental something there is. A sea of quantum potential, a canvas of mathematics waiting to express itself, a realm where laws emerge and time unfolds. If so, then the question, how did something come from nothing, transforms into how did the hidden richness of what we call nothing blossom into the universe we see. This idea doesn't strip the mystery away, it deepens it. If nothingness is unstable, if it inevitably gives rise to something, then perhaps existence is not an accident but a natural consequence of the most basic state of reality. Or perhaps the very distinction between nothing and something is an illusion, a limitation of human thought. Maybe the two are not opposites but different aspects of the same underlying truth. And in this closing reflection, there is room for both science and philosophy, for awe and humility. Science pushes us to uncover the mechanisms, to model the processes, to measure the ripples of the Big Bang and the signatures of particles. Philosophy pushes us to ask the ultimate why, to question the meaning of existence itself. Together, they remind us that the mystery is not a void but a source of wonder. So perhaps the answer to our original question is this: matter came from nothing because nothing was never truly empty. It was a cradle of potential, a stage where the laws of physics, or mathematics, or something deeper than both, could spark the emergence of a universe. From that subtle beginning came galaxies, stars, planets, life, and us, beings capable of standing in or before the cosmos and asking how it all began. And maybe that is the most important key of all. Not that we can fully solve the puzzle, but that the puzzle itself inspires us to wonder, to imagine, and to seek. The fact that we exist to ask is part of the answer. We are the universe reflecting on itself, matter born from mystery now gazing back into the depths of that mystery. So we end where we began, with the great question: how can something arise from nothing? The journey has shown us that maybe nothing was never nothing, and in that realization, we glimpse the possibility that the key to everything has been there all along, woven into the very fabric of existence, waiting for us to notice. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.